So welcome everyone to the workshop on Bayesian Predictive Inference. We're going to start off with two tutorials by Sandra and Lorenzo. We'll have a brief coffee break, and then we'll have more contributing sessions. Just a quick kind of add, there's a typo on the website. So we finish at 6:30, not at 7:30. So I hope Bernardo didn't prepare a 1 hour presentation. Okay, great. So we're going to start off with a tutorial by Sandra Porti. She worked along with Sonic Controller to set up the foundation support all the Sandra Porti with Bayesian stuff. Huge inspiration for my entire work. Sandra is an associate professor at the University, and she's going to be sharing with us today about the theoretical foundations of predictive inference. Sandra, you have 15 minutes each, and then we'll have some time.
Thank you, and thank you for the invitation. So feel free to interrupt me at any point if there are questions, if something is unclear. This is joint work with Sonia, and it is on a recent paper of ours in statistical science. Okay, so we are going to talk about the predictive approach to Bayesian statistics, where the focus shifts from parameters and prior distributions to predictive distribution. And this approach sometimes is referred to as post-Bayes, where, okay, I don't like this name, but I interpret this name as post-Bayes rule, okay? But actually, the perspective here is really a Bayesian perspective, because it's based on coherence, updating, and prior knowledge. So exactly as in Bayesian statistics. So I'll try to make you understand the connection, the foundational ideas between Bayesian statistics and this predictive approach. Now, I have to say that in this talk, I will focus on a very, very simple situation, so independent observations, homogeneous from an unknown distribution. Of course, things can be extended to more general situations, but I would like just to give the main ideas. Now, to understand how the predictive approach is related to Bayesian statistics, I will start by comparing the Bayesian approach to statistics and the frequentist approach to statistics, to understand what's the main difference. So let's start with the frequentist approach, where the frequentist approach estimates an unknown distribution through a database estimator. So the frequentist approach distinguishes between aleatory uncertainty, so randomness, intrinsic randomness, coin flipping, and epistemic uncertainty, so lack of knowledge. So the parameters are unknown, and that's not intrinsic in the frequentist view. That's not intrinsic randomness, that's lack of knowledge. So in the frequentist approach, parameters are fixed but unknown, and the uncertainty about parameters is epistemic. Now, in the Bayesian approach, starting from the early papers on Bayesian approach, the situation is different. So if we take the basic scheme, so Bayesian approach assigns a prior distribution to the unknown probability distribution F, and then it updates the beliefs using Bayes' rule to get the posterior distribution of F given the data. And in that case, probability theory models all kinds of uncertainty. So both randomness and epistemic uncertainty. So it's quite different. So the two approaches may look similar, but actually they're quite different. So we can see Bayesian statistics as a learning process. So first of all, the probabilistic model gives a model for both observations and parameters at the same time, And what is learning? Learning is conditioning on the data. So in that case, that we are considering, so homogeneous observations coming from an unknown distribution, the unknown distribution f is treated as an unknown variable. You all know this. Let's say from a prior distribution, let's say pi, that expresses prior uncertainty, and then given, so conditionally on that unknown distribution, the data are IID from F. So that defines the joint distribution for the unknown distribution F tilde, okay? I use F tilde to stress that it's a random distribution and the observation. So we have a probabilistic model which is defined on the product space. Parameters, or in the non-parametric case, the distribution function and the observation. So we have a joint distribution. So there is no formal distinction between parameters and observations. Everything is random. And that's the reason why, although there are many different techniques, basically what is an estimate? An estimate is just conditioning, so it's an exercise in probability based. Now, if we take again our basic model with observations that are conditionally IID, so we have this joint distribution for the random distribution F tilde and the observation, then we know we have a joint distribution. And if we marginalize that joint distribution over F tilde, the unknown distribution, we have the distribution of the observations. But actually, the random probability distribution F tilde is a function of the observations. And we can see this in a very simple way because it's the limit both of the empirical distribution and of the predictive distribution. So it's, let's say, measurable, it's a function. And that means that once we have given the distribution of the observation, everything is fixed. Also the joint distribution of the observations and of the unknown probability distribution. So Bayesian model is fully characterized by the joint distribution of the observations. And okay, that was also a reminder this morning. We know that by the finite representation theorem, our simple scheme, so the xi conditionally IID given a random probability distribution F tilde is equivalent to the sequence xn being exchangeable. So the law of xn being invariant under finite permutations of the indices. So the finite theorem suggests an alternative way of assigning this model, which is specify directly the distribution of the observations without bothering about the prior. And this is in contrast with frequentist modeling, because in frequentist modeling, the probabilistic model only describes the way that data are generated. So it only describes the aleatory uncertainty, not the epistemic uncertainty. While in the Bayesian approach, the probabilistic model on the observation models both aleatory uncertainty and epistemic uncertainty. So even under random sampling, the observations are not independent because, of course, observing x1, xn gives information on the future observations. Okay, so there is no independence, as we know, they are only conditionally independent. Now, what is the advantage of directly specifying the distribution of the observations as an exchangeable law? Now, first of all, it eliminates the need to assign a prior distribution to parameters that lack a clear interpretation. Because, of course, we know what are the observations. So in a way, it's more coherent to give directly the law of the observation because we know what they are. However, notice that the prior distribution is still implicitly defined. As we have seen, it is the limit of the empirical and of the predictive distributions. Now, in practice, assigning the law of a full sequence of random variables in a way that it captures both intrinsic aleatory and epistemic uncertainty is challenging. It's not easy, it's challenging. But we know that there is a simpler way of giving the distribution of a sequence, which is through the sequence of the predictive distribution. And there is this very nice result, UNESCO2-chair theorem, that is very general and tells us how to build the distribution of a sequence of random variables in general. Now, the space here is a very general space, a measured space, we don't even have the request for the space to be polished. And what we need to build a distribution of a sequence of random elements in this space is just a sequence of kernels. So we start with a probability measure P0 on X, and then we have a sequence of kernels. Kernels simply means that they are both a set function, so Pn of A, and also of x1, xn. And there are only two very, very basic requests. So with respect to A, that's a probability measure for each n and for each x1, xn. And for each fixed A, that's a measurable function. So very, very weak assumptions. And under these very, very weak assumptions, by this theorem, we know that there exists a law of a sequence and also a sequence with that law, such that Pn is the conditional distribution of xn plus 1 given x1, xn. So we can build the distribution of a sequence of random elements in very general space by giving a sequence of kernels. And we are completely free, unless we want some property, particular property, to assign those kernels. There are no constraints. And now, what is the approach? What is the advantage of using predictive distribution? That predictive distribution naturally reflects epistemic uncertainty. So when I give Pn, I am expressing my subjective opinion, given what I have observed, about the distribution of next observations, which is easier than giving the joint distribution. So in this perspective, what is a predictive distribution for a sequence of random variables? Is not a physical mechanism generating xn plus 1 from past data. It's not describing this. It is describing a learning rule. So how we learn based on what we observe. Okay, so that's Pn, our predictive distribution. And this approach is generally called predictive modeling. So we give a model through predictive distribution. So in predictive modeling, reasoning focuses on observable quantities. We have observed x1, xn, and what we expect about xn plus 1, what we have learned. And notice that predictive modeling is also intriguing as a form of Bayesian learning without a prior, because we don't need a prior here. Although, if the sequence is exchangeable, the prior exists, okay? But we don't need to give it. Now, here is a very, very simple example. Everybody knows it. It's just a podia urn, but just to show how learning is represented in that case. So the space here is 0, 1. So we have binary random variables. We start by giving subjectively the probability that the first observation is 1. Let's say alpha 1 divided by alpha, 2 numbers. And then after observing x1, xn, the probability that next observation is a 1 depends on how many ones we have observed. So basically, we reinforce the probability that next observation is a 1 each time we observe a 1. Okay, so that's a reinforcement learning. And we know that this scheme defines an exchangeable sequence. we also know what's the prior, and okay, and so we can also compute everything. So here, learning occurs through recursive prediction updates. We update our belief at each new observation. So we increase or decrease the probability of one depending on what we observe. Now, of course, UNESCO-Tulcea theorem gives a way of defining the law of a sequence, but what about if we want the sequence to be exchangeable, okay? So what constraints must the sequence of kernels satisfy in order for the sequence to be exchangeable? So what should we do if we want an exchangeable sequence? And the answer here is quite simple. So there are only two conditions on the predicted distributions that ensure that the sequence is exchangeable. It's an if and only if, actually. So the sequence is exchangeable. If and only if, first, which is quite obvious, the predictive distribution must be symmetric with respect to past observations. Okay, so basically, it does not depend on the order of past observations, the predicted distribution for next observation. The second condition is less obvious. So given past observation, next two observations must be exchangeable, okay, just two. So these conditions are necessary and sufficient for the sequence Xn, whose distribution is defined through the kernels, the predictive distribution, to be exchangeable. So if we want to specify the distribution of a sequence in such a way that the sequence is exchangeable, we need to specify the sequence of kernels in such a way that they satisfy those two properties. Okay, so this is, again, a very, very well-known example of predictive construction, which is the Podia sequence that describes a construction for a sequence which has a Dirichlet process prior. And that's similar to the previous example with binary observations. So we start with a distribution P0 on our space. Here the space is a Polish space. And then to specify Pn, again, we have an equation that depends on what we have observed. As you can see, it's symmetric in the observations. And we can see easily that this is a convex combination between P0 and the empirical distribution functions, with weights that are alpha divided by alpha plus n and n divided by alpha plus n. So again, we take into account what we observe, and if we consider set A, the probability that next observation is inside A depends on how many observations in the past we have seen in that set. So again, that's a reinforcement learning. And there is also an urn description that we can use. So we start with an urn that only contains black balls. And then we pick balls from the urn, and then we return the balls to the urn. And each time that we pick a black ball, we generate a new color from a color distribution, which is exactly P0. And then when we take a colored ball, we return the ball into the urn together with another ball of the same color. So we have that visualization of the reinforcement. This is another example of predictive construction. Now, this is in a way similar to the Podia sequence, but the point masses, delta xi, are spread with a kernel. So instead of reinforcing just the points, here we reinforce, let's say, points near, close to what we have observed. Okay, this is in general not exchangeable, unfortunately. It is exchangeable only in the case where the kernel is a very specific kernel. So it's just P naught, the distribution of the colors, conditional on a sigma algebra G. And in particular, if the kernels are absolutely continuous with respect to P naught, basically the definitive measure, so the prior, corresponds to a mixture model where the components have known disjoint support. So basically, random histograms with known bins. I think that this is a very interesting example, first of all, because it's a very simple construction, but also because, as you can see, this is exchangeable only in a very, very specific case. So we can start thinking that maybe exchangeability is maybe too strong, and maybe we can think about relaxing a little bit exchangeability to get more flexibility. And so the question is, how can we relax exchangeability still in the framework of homogeneous observations? Okay, so in a way, I think that all future observations given the past come from the same distribution. So we would like to relax exchangeability, but still keeping that idea. And to answer this question, we can see how we can describe exchangeability. And there is this nice description of exchangeability by Kallenberg in 88. So it's immediate to see that an exchangeable law is stationary, okay? Stationary, so it has this property, an exchangeable sequence is stationary. And there is another property, which is that the observations are conditionally identically distributed. That means that given the past observations, x1, xn, all future observations are marginally identically distributed. So this PID condition represents exactly what we have in mind, that there is some homogeneity. Given what we have observed in the past, so we have some knowledge, we think that all future observations come from the same distribution. And the result that I was mentioning by Kallenberg gives that very nice characterization of exchangeability. So a sequence of random variables is exchangeable if and only if it is both stationary and CID. Okay, so these two conditions are equivalent to exchangeability. Here, stationarity means strong stationarity. Okay, so the distribution, the joint distribution doesn't change if we start looking at the observation at time 1 or 10 or 100. Okay, it's strong stationarity. Now, if we want to keep the CID condition, what can we do? We can give up stationarity if we want to be a bit more flexible and give up exchangeability. So, as I said, under the CID condition, all future observations share the same conditional distribution given the past, so they are homogeneous in our opinion. And in fact, it is sufficient that next two consecutive observations are the same distribution given the past. That's a sufficient condition. That's equivalent to the CID condition. And that's a very nice property, because then we can equivalently express the CID condition by a martingale property. So the property that next two observations are marginally identically distributed given the past is equivalent to, and the proof is just one line of property of conditional probability, it's equivalent to the sequence of the predicted distributions being a martingale measure. And we know that martingales have very nice property that we can exploit. Now, question, how close is that condition of CID to exchangeability? Is it far? Is it close? Now, CID sequences have very nice properties. First of all the observations are marginally identically distributed. So they have the same distribution. As we have seen, the sequence of the predictive distribution is a martingale measure, and it converges. It's a martingale, so it's not surprising that it converges to a random probability measure, F tilde. And if you remember what we have said about exchangeable sequence, that's a property of exchangeable sequences. For an exchangeable sequence, the sequence of predictive distributions converge to the so-called directing random measure of the sequence, F tilde. And we have the same property. Then, using, again, martingale methods, it's not difficult to see that also the sequence of the empirical distributions converge to the same limit as the sequence of the predictive distributions. And again, this is a property that CID sequences share with exchangeable sequences. So predictive distributions and empirical distributions converge to the same limit, which is a random probability measure, exactly as in the exchangeable case. Of course, in this case, observations are not conditionally IID given F tilde. Okay, that's no more true because we don't have definitive representation theorem for CID sequences. And now there is a nice property that is a general property of sequences that whenever the sequence of predictive distributions converge to a limit, which is again a probability distribution, then the sequence is asymptotically exchangeable. So if we take the sequence starting from time n or n+1, and then we take the whole sequence, that converges weakly, almost surely, to a sequence Z, which is exchangeable. And that sequence Z has exactly the directing random measure F tilde, which is the limit of the predictive distribution and of the empirical distribution of our CID sequence. Okay, so same limit. So, of course, a CID sequence is not exchangeable in general, but still, as n becomes large, the distribution, the joint distribution of the observations becomes closer and closer to exchangeability. So it's not too far from exchangeability, at least asymptotic. And we can take this F tilde seriously, and we can call this F tilde the directing random measure of this CID sequence, and its distribution, in a way, is a prior, okay? Because again, if you think that F tilde is the limit of the empirical distribution, it's clear that it represents the distribution of the observations. Okay, we take the empirical distribution, we have homogeneous observation, they are identically distributed. And of course, the empirical distribution represents the distribution of the observation. So we are interested in that limit F tilde. Okay, here is a very simple example, which is again an extension of the Polya sequence. It's very similar. The only difference is that now the observations are weighted. We put weights that are positive random variables, and under the assumption that the weights are conditionally independent of the observation, so Wk is conditionally independent of xk given the past. Under this condition, this sequence is CID. And for example, a scheme like this could be used in the case where we trust some observations more than other observations, so we want to weight them more. Okay, we know that this sequence is CID, and therefore there is convergence of the predictive distribution, of the empirical distribution, and it's asymptotically exchangeable, although it's not exchangeable unless the weights are all the same. Okay, now if we want to use CID sequence, we have a problem. We know that there exists a limit of the predictive distributions, which is also the limit of the empirical distribution, but we don't know what's its law, what is its distribution. So we don't know the prior law and we don't know the posterior law. We just know that F tilde exists. So what can we do if we want to understand? We have some data and we want to find the posterior distribution, so the distribution of that limit F tilde given the data. Now, one thing that we can do is sampling. So we can simulate from that distribution. And the simulation is very easy because we can use the predictive distribution. So we start, let's say, now I'm considering real valued random variables just to keep things very simple. And so suppose that we want to generate a sample from F tilde at the points T1, Tk that are fixed, a grid of points. Okay, so I want to simulate from that random distribution. And I have some observations, x1, xn. So what can I do? I can start by sequentially simulating observations using the predictive distributions that I have, okay? So I start with xn plus 1, I sample xn plus 1 from the predictive Pn, and then I have new observations. I put the observations inside my sequence of observations, and I go on, and I generate xn plus 2, and so on, until xn with, let's say, capital N with a large n. And now, see, if capital N is large, I have a large sample. And since we know that the predictive distribution converges to F tilde, instead of the limit, I can take the predictive distribution, Pn, that depends on the observation that I have simulated, as representing F tilde, okay, which is the limit. And if I repeat these m times, then I get a Monte Carlo sample from the posterior distribution. Okay, it's the posterior because I start with a sample x1, xn. So I get a sample from the posterior. Okay, this is something we can always do, but if we have a large sample, so we are in a world of big data, maybe we have a lot of data, we can even give an asymptotic approximation of the posterior without any simulation. Okay, so we can start from the last equation. So the distribution of F tilde at the point T, which is a random variable, given x1, xn is asymptotically normal under some conditions which are weak conditions. It's asymptotically normal, so for n large is asymptotically normal. That means that actually there is convergence to normal distribution once suitably normalized. And the normal distribution is centered at the predictive distribution, but the predictive distribution is also the conditional expectation. We have seen that the predictive distribution is a martingale. We are in the CID setting, okay? So the sequence of predictive distribution is a martingale. So Pn is also the expectation of F tilde of T given x1, xn. So it's centered in the, let's say, posterior expectation of F tilde of T, and we can estimate the variance, and the estimate of the variance, that VMT, which is written there, only depends on the predictive distribution of past observation. So we know it, we can compute it, it's an estimate. Now, the rate of convergence depends on that sequence alpha n, which is a normalizing sequence for the squared predictive updates. What are the predictive updates? Each time I have a new observation, I update my predictive distribution. I have an update, right? And now the alpha n basically say how large is the predictive update. The predictive updates must go to 0, then goes to infinity because Pn converges. And alpha n depends on how fast these predictive updates go to 0. Okay, that's only a sketch of the result without all the details, but it's a general result. Now here the result is given only at one point t, but actually you can give it at a grid of points, and we are actually working to extend this to. And if you listen to Sonia talk, on Tuesday, we have results for the convergence of the process. So if n is large, instead of sampling, we can just use that approximation, that normal approximation. And therefore, we can, for example, build asymptotic credible intervals for f tilde of t, our random probability distribution f tilde at the point t, we are in R, so that's the distribution function, with probability at least 1 minus alpha is between, okay, that's an asymptotic result, is between Pn minus Z is the quantile, times the standard deviation, plus or minus this. Okay, so we have a way of writing asymptotic credible intervals. Okay, and that's a comment that I was already telling you. So the rate of convergence, and so also the dimension of the credible intervals depends on how fast the predictive updates go to 0. Now, notice that this is not a result like Bernstein von Mises. In Bernstein von Mises result, we have an approximation, a normal approximation of the posterior distribution, and for exchangeable sequences, but under the assumption that the observations are independent and identically distributed from a true distribution, which is not what we are doing here. Okay, there's just an approximation of the predictive distribution of the posterior distribution, but our observation comes from the model itself. So it's just, the goal is different. So the goal here is to just provide an asymptotic predictive based approximation of the posterior distribution for sequences that are not exchangeable but are CID. Of course, that includes also exchangeable sequences. And consistency properties and contraction rates are interesting problems. We are doing some work on this. Still, I think, quite open problem, interesting problem. Okay, and now let's see how can we give predictive distribution. So how can we construct our sequence? Now, one way of simplifying the problem of assigning predictive distributions in general is through predictive sufficient statistics. So we have our observations, and if the predictive distribution depends on past observations only through a function of those observations, then that function is called predictive sufficient. Now, what happens in the case of exchangeable sequences? In the case of exchangeable sequences, the predictive distributions we know are symmetric with respect to past observations. And that means that the predictive sufficient statistics must be a symmetric function of x1, xn. And therefore, we can also express the predictive sufficient statistics as a function of the empirical distribution of x1, xn. That's exactly the same. So now, if we stay in the case of exchangeable sequences, that's a way of getting parametric models. The intuition is quite clear. So here I'm considering an exchangeable sequence, okay? And the idea is quite simple. We know that, so here hat Fn is the empirical distribution. And we know that the empirical distribution converges almost surely weakly as n goes to infinity to the directing random measure, f tilde of the sequence. Now, if T has some continuity property, I don't give mathematical details here, but you can read on this paper if you are interested. So if T is continuous, we can expect that T of hat Fn converges to T of F tilde. And if also Qn has some, let's say, uniform continuity property, it will converge to a limit function Q. So on one hand, Pn converges to a function Q of T of F tilde. But on the other hand, Pn converges to F tilde itself. And therefore, F tilde must be exactly the same as Q of T of F tilde, which means that T of F tilde is a parameter of our distribution. So we have a parametric model. So in the case of exchangeable sequences, we can characterize parametric models by predictive sufficient statistics. And in particular, if the predictive distributions are dominated by the same measure, lambda, which is a general measure, and the convergence of the predictive is a strong convergence, so not weak, but in total variation, then the model is also dominated. So we have a dominated parametric model. And now we want to extend this idea to CID sequences, or maybe also sequences that are even more general than CID sequences. And we can use sufficient statistics to simplify the assignment of the predicted distribution. Here, when I say sufficient statistics, so in the previous case, I was thinking to a statistic taking values in a finite dimensional space, but here is a general statistic, so it can also be an infinite dimensional space. So how can we simplify the assignment of predicted distribution through sufficient statistics? So suppose we have a sequence Tn of random variables. So Tn depends on the past observations, and there is a simple way of updating Tn. So we have a situation where Tn is a function only of the previous value, Tn minus 1, and of xn, and hn is a simple function. That means that we can store only Tn. We don't need to store all the information about the observations. And there is a very simple way to compute the new value of Tn once we observe the new observations xn. And then suppose that Pn is a function Qn of Tn. So we have again a sufficient statistic. And of course, that's a general scheme, and then you need to specify Qn, to specify Hn to have a model. Now, in many common Bayesian models can be written in this way. And here are very, very simple examples. The first example is again the two-color Polya urn, 0, 1, that we can write recursively. Here Tn is the sample mean. And there is a very simple way of updating the sample mean, and you don't need to keep track of the observations. You just keep track of the sample mean, then you take the new observations, and you again compute the new value of the sample mean. And then Pn, so the probability that next observation is 1, is a very simple function of the sample mean. So the previous scheme. And that can be generalized also to the Dirichlet process prior, the Polya urn. And again, here, the sufficient statistic is the empirical distribution. So we are in a non-parametric situation. Here is another example called measure value Polya sequence, where we have a scheme which is in a way similar to the Polya sequence and also to the kernel-based Dirichlet processes. So Pn, so the predictive distribution, is a normalized measure. And the measure, which is the numerator, gamma P naught plus sum of Rxi, is the sum of gamma is a constant, P naught is a probability distribution, and then we have these kernels, Rxi, that are measured. They're not requested to be balanced, meaning that the measure of the whole space can be different depending on the observations. And we can also, in this case, consider this construction as an urn process, where we have colors, and we start at the beginning with some mass for each set of colors B. And then at each step N, the set of colors B receives an additional mass R that depends on the observation Xn. And in general, this is not exchangeable, and basically it is exchangeable if and only if it is a kernel-based Dirichlet sequences that we have seen before, and therefore that means in particular that the reinforcement must be balanced. Now I'm going to show 2 more examples that are built in a very, very simple way. So we have taken 2 algorithms. In the first case, this is Newton algorithms. In the second case, it will be the online gradient descent. And we reinterpret those algorithms as learning rules. So we take them seriously. So we build a learning model using algorithm that already exists. So in this case, the algorithm is Newton algorithms that was proposed, an approximation of the Dirichlet process mixture model to simplify computations, because it's very fast. Okay, it can be computed very fast. So we have a mixture model with a kernel K, with K is a density with respect to a measure, lambda, whatsoever. And then we update the mixing distribution Gn using Newton's algorithm that you can see there. So where Gn is a convex combination of the previous mixing distribution Gn minus 1 and of, okay, what is that? That's Bayes rule. So that's the posterior distribution, okay, that part is the posterior distribution for just one observation, Xn, when the prior is Gn. Okay, that's Newton algorithm. It's very fast, it's consistent, it has good properties as an algorithm. So it's a good algorithm. Okay, we have taken a good algorithm, but now we interpret that algorithm not just as an algorithm, but as a learning rule. That means that at each time we observe and send a new observation, we update the mixing measure, and then we say, right, what do I expect for next observation? My predicted distribution, Pn, is a mixture model with mixing Gn. Okay, so we take it not as an algorithm, but as a learning rule. And what's the advantage of taking it as a learning rule? That now there are properties So the sequence of observations is CID, conditionally identically distributed. So all the properties that we have seen so far, GN converges to a random mixing distribution, okay? Because we are in this setting, that's a learning model. And that means that the sequence is asymptotically exchangeable. There is a prior distribution, there is a posterior distribution, and we can measure uncertainty. And we can sample to approximate the posterior distribution, and we can give an asymptotic approximation for the posterior distribution when n is large. So it's not exactly exchangeable, but it's not far from exchangeable. And what's the advantage with respect to, for example, a Dirichlet process mixture model? That is very fast to compute, very, very fast to compute. The second example is based on, again, an algorithm. Here the algorithm is called online gradient descent. So here the situation is quite simple. We have a problem of binary classification. Y can be 0 or 1. And we model Y by a logistic regression. We have observations Xn. So Xn is a feature vector. So then we have the model for X and Y, okay? Let's say that the distribution of X is known, or we can estimate it in some way, and then the conditional distribution of Y given X is a logistic regression. And then we learn about the parameter of the logistic regression by the online gradient descent algorithm that takes the current value of the vector of parameters and moves a little bit at each new observation in the direction which is opposed to the gradient of the loss function. So at each new observation, we move a little bit to minimize the loss function, okay? And again, this model has nice properties. It's not CID, but here there is still a martingale, which is beta n. Beta n is a martingale. So the sequence of parameters converges to a random vector beta tilde, which is in a way our unknown random parameter. So the sequence beta n is a martingale, so beta n is exactly the condition expectation of beta tilde given x1, xn, y1, yn. The sequence is still asymptotically exchangeable, okay? That's due to martingale properties, and the directed random measures satisfy what we want. So the conditional distribution of y given x with respect to directed random measure is a Bernoulli distribution with parameter g of x beta tilde. And again, we can sample and we can give asymptotic distribution for our for the posterior distribution of our parameter beta tilde. So again, we are not too far from exchangeability. Okay, that's almost the end. So just to wrap up, a Bayesian paradigm provides a powerful framework for learning from data and performs well. So I'm not saying you shouldn't use exchangeable sequences. That's what not I'm saying. But we can see also the usual Bayesian paradigm as a learning process. And we can also extend these ideas from exchangeability to more general constructions, and we get flexibility, and we get sometimes more interpretive models, and we can simplify the computations. Of course, there are many open questions. Among these, the study of consistency, contraction rates, and extension to more general models. Thank you.
I think we have some time for some questions. Okay, go ahead, Steve.
Just
Can you? The mic. Thanks.
The question, but maybe it's more of a comment, is when I listened to your entire talk, I didn't see anything that was not Bayesian. As I was puzzled by the suggestion that it's post-Bayes or different than Bayes. I mean, there are a lot of versions of Bayesian models, and there's no reason that they need to be exchangeable. You've written down the sequence, a model for a joint distribution, and you're using Bayes' theorem to do the updating. Seems exactly Bayesian.
It's exactly Bayesian. The point is that there is no product.
Well,
No explicit product.
no, it's supposed to be.
Yeah, no explicit product. Yeah.
You know, and yet,
But it's
certainly when I was in graduate school, I went to Minnesota with Seymour Geisler, who ran huge predictors. And he would always speak of parameters as useful fictions. And say, you know, we'll write them down because it helps us do a calculation. But fundamentally, we're interested in X1, X2, X3, and so this is very much in line with that view.
absolutely.
Second view that I also learned is that that both evolutionary and epistemic uncertainty should be treated very, very seriously. And that you can essentially do right on a frequentist model, classical model, and then use the Bayesian part, prior distribution, just to express uncertainty about fixed but unknown quantities. And I think it's very important for Bayesians to talk to scientists that, you know, are interested in, you know, the weight of a subatomic particle or something. And I don't think I want to tell people it's random theory. I think they want to tell them it's a fixed but unknown quantity. And what we're going to do is express some uncertainty about the quantity by means of descriptions, the language, run a certain probability. So I would hesitate to separate from Bayes. So I think everything you're doing fits within the frame. It's built within a brilliant.
Yes, absolutely. Yes.
Sandra, so just a curiosity, so your prior does not exist unless to the limit. But can we, I mean, define Bayesian and typically fix the prior in such a way that I can specify some characteristic, I don't know, the prior mean, the prior variance, does make sense also with this predictive approach to be able to be likely to specify some of the characteristic of the prior?
So if a parameter has some meaning coming from the data, those properties of the random parameter maybe can be considered as a property of the data. So, yes, I think that maybe they are connected, just parameters are, no, we are interested to the mean of the distribution, so you know what it is also in terms of the information.
We have for any number. Thanks for the talk. It's a short question. I don't see a reason looking through your formulas for sensor observations and survival methods to not fully comply to this framework. So I would like, and this would be nice to have those consistency results for survival models very easily. So I'd like to know if this is a line of research that exists, you know, about survival models in the setting and such and such. Thank you.
Honestly, I don't know.
Yeah, sorry.
I don't know. Yeah. Sure, it's interesting. Interesting.
Okay, great. So let's see if Sandra has another insight. That sounds fine. One time.
What is it? Okay, here. Yeah.
Uh,
Perfect.
Great. So next up, we have this wonderful talk from Sandra about kind of the foundation underlying Lorenzo Capello from University of Alabama. Now I'm talking a little bit more about kind of practical rigorous methods sort of debates. And if I'm right, these will really do quite far from these, but still retain some of you. So please welcome Lorenzo Capello with Sandra.
Okay, thanks, Edwin. Thanks for putting this together. Thanks to the organizer in general to put this wonderful conference together. Thanks to Sandra as well for the nice introduction. She kindly shared also the presentation a few weeks ago, so I had a little bit some help to prepare for today. So the idea is continuing along the line of the second part, essentially, of Sandra's talk, to keep giving some example of what kind of predictive schemes we can look at. So we are in this context. I think that by now everywhere it's quite clear. It's the predictive workshop. I took a screenshot from Edwin Royal paper, which I really like this picture because it's kind of this cartoonish version of what we're trying to do now. So we have a parameter of meters. It can be finite dimensional or infinite dimensional. And in this world, we are kind of lying in this green box. No? So we are usually used to go from left to right. So to define the model a prior and then quantify the uncertainty about the unknown quantity. Even in this case, could be also the data generating mechanism, no? But it would be a fixed parameter. In this world of predictive inference, we're kind of going the other way around. We are specifying something on the observables. Hopefully hoping that in some contexts it can be easier to have a computational advantage and somehow reverse engineering. So going from prediction to inference in a way. No? While specifying the predictive over the full process could be quite hard for the observation that we're missing, generally the way that we go about it is specifying the sequence of one step ahead. And in practice, the sequence of one step ahead, we specify them with a map that essentially tells you how to take the last predictive update and how to incorporate a new observation. So there are two ways. Sandra gave us an explanation of what are the two approaches essentially to go read in this green box, to go from prediction to inference. One is based on asymptotic result, so we can use kind of central limit theorem for Martingale essentially, and we approximate this posterior. Another scheme is, let's say, something that very much resembles the spirit of the bootstrap. I think that in Sandra's slide, a predictive simulation-based inference scheme. You know, it's essentially really at the heart of it, there is really a bootstrap in the Bayesian spirit that requires a few ingredients, some practical and some that are really at the heart of the mechanism. So one is this learning rule, how I'm going to update this prediction. And then I need to find a way how I'm going to estimate my quantity. Like if I have a parameter, I really need to choose an estimator. If what I want to report is uncertainty over the data generating mechanism, essentially like I have an identity. So I need some data to get started, and then essentially I have a bootstrap type of parameters. Because the way that these schemes start, essentially like I initialize my predictive, giving the data, and then I repeat, possibly in parallel. That's why there could be some computational advantages in doing this. The following, I am recursively generating synthetic data from my predictive. I am generating data and updating. That's why, let's say, we use this map where at every iteration we are recursively incorporating this. After having done this, I compute the value of my statistics quite essentially using both my real data that I collected and the synthetic one that I generated. I do this many times, and one hopes that the histogram of my estimate resembles or gives me a way to provide the measure of uncertainty application that I'm looking for. And in some cases, we can show that this scheme is exactly the same that the construct exactly predicted. So this is really like a bootstrap type of idea. I think that here the twist that is being enlightened by these papers on early papers on predictive inference is that we have a lot of freedom in this part. Like in the bootstrap, we are used to work with empirical distribution. Here, essentially, right, we are free to elicit a different type of tree. So one example, so just we are going to receive some of the examples that Sandra measured. For example, one example is the predictive distribution of the iteration process. So here we are working the realm of the empirical. At every iteration, I'm giving the update using the point mass at what I observe. Somewhat in the tradition of the post-division process paper, what's going on that in order to bypass the discreteness of the DD update, people have been working on a lot of continuous update, and we're going to see a lot of them in the next 45 minutes or so. So in the tutorial, I think that to me, the general theme to me was like, we have a lot of freedom to decide this predictive update. So I kind of try to put myself in the shoes. You want to come up with your predictive update. Can you do this simulation testing? So we are gonna work a lot around the two questions. So the first one is, how do I come up with one? We already seen some examples with Sandra, but I think that is gonna be illustrative to go through a few. So the first class of approaches, I can take them from a Bayesian model. For example, the division process. I kind of argue that in this case, it is a less interesting type of cases because once we have the predictive distribution of a Bayesian model already in closed form, we might already have the measure of uncertainty quantification in closed form. But there is a closely related family, which is the idea of mimicking the predictive distribution of a Bayesian model. So we have a few algorithms that try to mimic the predictive distribution of the division process mixture, and that led to at least two, and we'll see more successful algorithms. And we are going to discuss both of them in the tutorial. One is the predictive recursion, which is Newton's algorithms. We are going to look at it just the simple derivation of Newton algorithms. I think that there are a lot of good lessons in the derivation of these algorithms that then are then translated to other algorithms, which is the Gaussian popular algorithms. In a way, like these are the two algorithms that are in the two Royal papers, one by Sandra and Sonia, one by Edwin and Chris and Stephen. So there is another class of model. One can think, well, you know, I have my own predictive schemes. I'm very clever. I came up with my own predictive schemes. So you can say, can I use it for predictive things? And you know, we're going to see one example. It's algorithms, I don't know, I call it any popular algorithms. I don't know exactly how it's called, but people that work a little bit with Copo, I think that are familiar with it. And then I think that there is the third line that to me is actually the biggest promise of this field, at least as a personal case. So we have this possibility to go from prediction to inference. There are entire fields that are based just on prediction, like people in learning theory and always in training algorithms to build algorithms that are good at prediction. People in machine learning have done the same. So that's another way. Let's say I take a random forest. Can I use the random forest to generate the fake data, synthetic data, and then put it in my simulation-based game? And we're going to see some example. So these are possible ways, and I think that we're going to try to cover some of these ideas. Then the second question, I think that is really nested. So both of questions are going to be answered together. Say, how crazy can I be? So essentially, like, can I take any algorithm and use it? So obviously, there are some properties that needs to be satisfied, you know, and because we are defining a sequence of predictive, so it needs to make some sense, you know. And Sandra told us a little bit about the probabilistic property that things need to satisfy. I use two names. So the probabilistic property, what I use between quotation marks, the validity of the mechanism. I'm going to refer that the sequence of predictives that I define is valid, meaning that the sequence of the synthetic data generated has some good properties. And essentially, like the property that we're going to try to check is asymptotic exchangeability, spirit of what Sandra from Sandra's tutorial. And you have two ways of checking this. So one is relying on the martingale property, and in this case we have the CID property, which is nice. And then toward the end of the tutorial, we're arriving in this world of beyond martingale. And I think that I'm going to look a little bit at the ideas of what is possible to do if we don't have the martingales. There is a second desiderata, which between quotation marks, I think the rule needs to be practical in the sense that we want to be able to implement these schemes. So we want to be able, at minimum, for example, we need to be able to generate synthetic data. We need to be able to do the update. And there are a lot of other numerical properties that happen. Right? The order dependence, does it require a grid? And these are all considerations that actually enter into the computational complexity of the algorithms. We are not going to talk too much about it today. Sometimes I'm going to give pointers, except the fact that given the title, everything is going to revolve around recursive algorithms, at least to guarantees this one. No? The recursive version of the algorithm at least guarantees that I'm going to have a big update. Okay, so that's the plan for the tutorial. I hope that is clear. So we start from an algorithm that we have already seen. And so all the algorithms that I'm trying to check to develop is algorithms on the observable, but we started from Newton algorithm just to highlight a little bit some freedom that we have to be able to do these schemes. So we start, the story starts with Divisory process mixer. And the Newton algorithms is an approximation of the predictive for the mixing measure. So not on the observable, on the latent quantity. So if you read the Newton original algorithm, or Newton original paper, Newton and Coase original paper, they start from the case that I'm given only one observation. I'm given only one observation. What can I do? Well, in this case, I can compute the Bayes estimate in closed form. It's not very hard, no? I am given a single observation. So I essentially apply the Tower property to augment the expectation with θ1. But what I have inside in the expectation, since this is going to be distributed according to the Divisory process, is the predictive of the Divisory process. So this one is available in closed form. The Bayes measure is fixed. I can take it out of the expectation. And so everything is kind of easy to compute. No, everyone here is good. So here just, if you read Newton's comments, it starts really pointing out a few things. No, they're saying, well, it's kind of similar to the kind of update that we are used to see in many Bayesian estimators. No, that I'm mixing between a prior guess and an update. And I note that Bayes' rule appears only in the second part, in the updates. No, essentially, like I have the likelihood, the prior, and the normalizing constant distribution. So when I go to n bigger than 2, we never really usually compute it. Like it's kind of a combinatorial argument. I was looking at Rose's paper. It's actually a combinatorial argument that actually we never go through. So what Newton suggests, so this is the argument that we have just seen with Sandra. So essentially, suggests to essentially mimic the rationale of the first Bayesian update of the one if n equal to n update. So I think that to me, at least, this was really essentially at the beginning of the research part of my PhD. It's usually well used that Bayesian models have quite some formalism the way that we compute quantity. Like there is a pretty strong set of mathematical rules. Here we are already deviating from it very quickly. No? It has really the spirit of building an estimator, no? Because we made a lot of choices. No? So for example, we fixed a deterministic sequence, and we decided to add it as a way to define this mixture between my best guess up to a time point and the only part in which I use the Bayesian update. The Bayesian update is the Bayesian update of n equal to 1 that I'm going to repeat recursively. And I'm going to choose alpha in order such that at some point the algorithm is going to converge. So I want to forget the initialization, and I want to have it such that at some point I stop updating. So since most of the things I'm going to write it with density, I just assume that the density exists, and let me just write the algorithms for the density, but it's just the same. And so just a few observations. So the algorithm is exact when n equals 1, and is clearly not when n is bigger than 1. So this is very obvious. There are some numerical considerations to put into place. So the algorithm needs to be evaluated in a grid. So I really need to discretize the theta and evaluate it on a grid. I need to do some numerical integration to compute at every step the normalizing constant. Despite, and most important is order dependent. So like it depends on the order of observation. So essentially, we already see that it cannot correspond to an exchangeable model because we don't have this invariance with the order of observation. Generally, I have to say that, especially like, you know, as I already PhD student, this idea of having an estimator that is order dependence, in general, is pretty scary. Except that in this case, definitely this algorithm is a big history of success. You know, it's incredibly accurate. People keep working on it. There are papers, you know, p-values that are using this. So the algorithm, whoever tried to use this algorithm, works extremely well for a very complex problem, no? And we can use it for predictive inference, you know, like we can use it, and this was already covered. So now it's a bit over, but our scope is a bit to focus on the observables. So we have already seen it in Sandra's scope that if I want to build an algorithm for the y, if I want to build an algorithm for the y, all I need is just to complete the list at the end of my output. No? And I can prove that this is a valid predictive update with a marking. What I want to point out is that if what we want is to build a scheme for the observables, this is quite a convoluted way to get a scheme for the observables. No? Indeed, if you read Sunny and Sondra paper, almost everything is about the more difficult problem of working with the mixed measure, not just with the mixed distributions. So now we are going to move to a scheme for the observable that bypasses numerical integration. Okay, so and here I went a little bit fast simply because it was already covered by Sandra. But what I want to point out of this section is essentially like the freedom that we have in the choice that we make. Like we took the predictive distribution of a Bayesian algorithms for n equal 1, and that's available in many cases. And somehow we made a lot of choices to kind of repeat it recursively. Like, and this has been thanks to Michael Newton, Zhang, and intuition by them. So let's move to, so the point is that we want something on the observables while going in modeling the mixed measure and then doing all these integration steps. Can we bypass it? And in order to bypass it, we need a first ingredient, which is the copula characterization, given by Richard Hahn, Ryan Martin, and Stephen Walker in a JASA paper. I don't think that is a case that Ryan Martin, that worked on the predictive recursion, then came up with these new algorithms. So we have a predictive density corresponding to a specific model that is parameterized by theta. Pi n is the posterior, and what we're going to do is we're going to take the ratio of consecutive predictive density. So I take the ratio of consecutive predictive density, I just rewrite it, and essentially here is exactly, I substituted at the numerator I just took the posterior temporal mass one, essentially I took out the Yn observation. No? You see, I have the normalizing constant, so these three terms here are the posterior distribution at time n. Okay, so I just rewrite it, and then I notice that what do I have? I essentially have at the denominator the product of two margins. At the numerator, I have a bivariate density where the dependence is determined by the posterior Fn minus 1. So bivariate density over product of marginal. Well, one can prove that if I integrate out one of the components of the marginal, I have one of the components of the variable, I have the marginal. This is exactly the definition of a copula density. So the ratio of predictive density, it is a copula density whose argument are the predictive distribution. When I say evaluated at y and yn, I mean the corresponding CDF. So this characterization essentially is old for any exchangeable sequence at least, and it can be a little bit more general than that. Quite essentially, so this is not very standard, because essentially we are saying that the Bayesian update is multiplicative, no? Like I can obtain the predictive density conditional and data point by multiplying a copula density times the previous predictive density. So we are not really used to this. We can prove other stuff. We can prove that the copula density depends only on the sample size. And note that essentially that if I have a sequence of predictive, I have a sequence of copula density. If my sequence of predictive density converges, my copula density needs to converge to the independent copula. So you need to have a 1 in the limit, no? So if n y converges, so this needs to generate into the independent copula. So at finite n, I could have any copula, but in the limit, I need to have an independent copula. So let's look at one example to fix a little bit the idea. So, simple example, we're going to see it some other time. Our model is Gaussian, we don't know the mean. We put a Gaussian prior on the mean. Everything is available in those form. So we know how to compute the predictive density. I take the ratio. I just apply the same definition that I have at the numerator. I do some calculation, and then essentially what you do here in practice is that you try to solve these integrals here at the numerator, and magically you need to go to look in the book of the copula that they are, and you will find that you have computed a Gaussian copula density. So in this case, for example, a Gaussian model, the ratio of copula is a Gaussian copula density. The Gaussian copula density has just one parameter, that is correlation parameter. So note that essentially it depends only on the sample size. As n goes to infinity, now I didn't put the formula of the Gaussian copula density, but you can imagine the correlation parameter goes to 0, meaning that I'm converging to the independent copula. Okay, so this is a good lesson. Because now we're going back to division process mixture. So I put it here at the top. So G is distributed for the division process. You don't see it, but it is there. So in our case, the model is a non-parametric model, so the unknown quantity that was indexed in my model is G. So I write the predictive for n equal 1, like we did for the predictive regression, no? And actually the formula that I have written here is essentially like the last one that I was complaining about in the predictive regression. No? Essentially like this, if you remove the kernel, is exactly the look that we had in Newton algorithms. But we know that a copula density needs to come out somehow, because for the previous characterization is valid for any Bayesian model, at least in the changeable world. So just to see it, let's divide everywhere by P0. So I divide everywhere by P0. And so where is the copula density? The copula density is everywhere to the right side. So we said that the ratio of predictive density is equal to a copula density. So this means that I need to look to the right side, squeeze my eyes, and try to recognize a copula there on the right side. Okay? So I don't know if anyone recognizes one. The example hasn't been chosen by chance, but here you should be recognized that at least this is a Gaussian copula. This is a Gaussian copula. And here I think that I put the one a bit consciously. We have an independent copula. So somehow it's weird that I have in the Gaussian model that was doing update to the Gaussian copula density. Now I have something somehow weaker, that I have the independent copula and a Gaussian copula, but it's here a copula, It's a copula mixture. It is the mixture between an independence and a Gaussian copula. So let me rewrite the algorithm. Now that we realize that we solve the copula, let's bring P0 again to the other side. So, and this one is update for n equal 1. So we have a mixture between my prior guess and a Gaussian copula density. Note that the need to compute the mixed measures has disappeared. But the lesson that we learned from the predictive recursion still apply. Like, what can we do? We have a bunch of things now that we have accumulated in our mind. We want to replicate the Bayesian predictive update recursively. We know that we need to converge to the independent copula. So we are going to do exactly this. So the form is exactly the same idea. So we take a sequence. We are lucky because we already have the independent copula in the mix. So we decided to use the sequence alpha n to derive the convergence to the independent copula. So I have a copula mixture. One of them is an independent copula. I'm going to use the alpha to derive the convergence to the copula mixture. And in this case, the authors decided to keep the correlation parameter fixed. So in the Gaussian example, we only had one copula, so rho is going to 0 to derive the convergence to the independent copula. Here we don't use this. But note again, these are arbitrary assumptions that we're like actually we see them in a work where rho actually goes the other way. It derives the convergence of the Gaussian copula to the point mass to make the update actually stronger as n plus 3. Again, there are, so mostly I think that what is important is that we bypass the need of going through G. No? So that's something a little bit to say that if I'm going for the observable, maybe this is a little bit more actionable. The rest is almost the same. The update is exact for n equal to 1, is not when n is bigger than 1. The algorithm is order dependent, so you can do something about it, but it's order dependent. You need a variable to compute it, but essentially we are moving all the numerical integration. Again, as an estimator, it's extremely accurate and it satisfies all the property to be used in predictive inference. Can we stop here? No, we don't need to stop. One gets greedy, and we take other models. So I will repeat always the same reason. No, like now we are not moving too much, but for example, I take a location scale. I write the update for n equal 1. I recognize the copula. Not big surprise is a student copula in this case. So I come up with a new algorithms. That is the same. So I learn a little bit of the art in doing that. And this art can be carried to many other models. No? Like for example, we have something this reasoning can be applied to the regression context to mimic the predictive or division process mixture of linear regression. We have a version with Steven that mimics the bivariate division process of Moyer and Walker. Like then you can build a factory of the algorithm like that. And one can show that, and we're going to see it actually, that this sequence is a martingale. So there are some lessons that one, a little bit out of experience, can see that just by mimicking the predictive of a Bayesian model, it's fairly easy to get a martingale. And this is not a surprise, because the predictive of a Bayesian models defines a martingale. So if I'm kind of mimicking with some art the predictive of a Bayesian model, I'm going to get a martingale. So the next question is, do we need, and these algorithms tend to be pretty practical. So the next question is, can we avoid taking a Bayesian model as a starting point? And let's see. So for example, what about that we understood that this, when in one case we had a Gaussian corpora, in another case we had a CDNT corpora. Let's just pick another corpora. Can we do it? So I just pick a corpora. In this case, theta just means that it's any corpora, I don't know, any corpora that you like. You know, sometimes can I use it, can I not use it? I don't know. In one work with Steven, for example, we took the Gamble corpora. We have some idea to think why that it should have a very good property. Is essentially like you implement the line of code. It's not really meant to represent anything except that I took a Gamble corpora, we called it in 10 minutes, we tried an example, and immediately we get a very accurate algorithm. So the question is, are these algorithms any good? So for example, we work with Steven and improve consistency of these algorithms. But as part of the tutorial is, it's excitement for the corpora. And it was right after 30 minutes. Can we use it for predictive recentering? So we need to check the validity of these algorithms. So let's try to check the martingale condition. So we need to verify the martingale condition essentially like for the semi-interval. Here, not beautiful, I just fix a set B. But we are trying to verify the martingale condition. So what do we do? Like, well, I have Pn times 1. I just substitute the definition of my Gaussian corpora algorithms. Here the integral appears because I'm evaluating a probability in a set B. I need to check it for some sets. We have this is the same integral, not the condition. But how do I proceed? Well, I have that PNV. So this object is a martingale as long as the expectation is equal to PNV. No? And so I try to check, is that quantity equal to PNB? So this expectation, the only random quantity is the expectation. So Pn are given the iteration defined by natural filtration. So the only random quantity is Yn plus 1, that is distributed according to Pn. So I'm going to solve this integral. So I have two marginals, a double integral, and my corpora. Now I apply the definition of the corpora, and I have a bivariate distribution with these two quantities as marginals. And so this is just the definition of the corpora that I define. The different corpora will differ depending on how this bivariate distribution is defined. Well, but this one and this one cancel out, and so it's almost trivial to see equal to PNB. So this means that that if I take any corpora, I have a martingale, so that means that the resulting sequence that I generate is CID. Actually, there is a recent work on the Electronic Journal of Statistics by Bissing and Walker that explore a lot around this idea of CID sequence and corpora. And so the connection is even deeper. So this means that when I was saying, is it valid? I take any corpora. Generally, these algorithms tend to be very accurate, and I get a valid update. In terms of practicality, well, you know, except for the grid, it's very fast to update. They are order dependent. I think that there is this extra set that I need to be able to sample from it. But here I think that we can read both the royal paper by Edwin or a recent one on quantile, and essentially you can see that it's very easy to sample from this Coppola algorithm. Potentially it's almost correspond like uniform sampling. So we are not going to go down this route that much, but it's very easy. Okay, so this one is beyond Bayesian model, but still, like we carry the reasoning of Dirichlet process mixture, Gaussian Coppola algorithms, and we move to Coppola. So the next question is, can I take algorithm from other literature? And maybe because in the department that I have now, there are a lot of people in learning theory, so I picked some old books from learning theory. I don't know, I could pick a book by DeVry, and I picked this one by York also. It's about regression, but there is a description of the algorithms. The first algorithms that it describes is the partition estimator. So here we are to John Tukey 47, so not really machine learning maybe, but you know, in chapter 25, there is the recursive version of the algorithms. This is just to keep it in the spirit of the talk. So how does it work? It's an histogram estimator. I think that the older one in the audience knows the histogram estimator very well. I didn't study the estimator a lot in my PhD, but I did now. So in the recursive version, we take a sequence of nested diagonal partition. I'm looking at a simple case where my state value 0, 1. So the nested sequence of the first partition is the interval 0, 1, and then between the other split. So how does recursive algorithms work? And I'm going to denote by ANX the cell where X falls. So I sample the first. So how is a recursive scheme can be inspired by an histogram estimator? Well, the first one is a uniform over 0, 1. The second point, I'm recursively using the first level partition and the second level one. So in this case, for example, Y1 fell in this box, so I'm going to have a mixture between the uniform in 0, 1/2 and the uniform on 0, 1. And I keep going, and I keep defining a recursive estimator, and I define this recursively. So this is essentially like a recursive version of an histogram estimator. Well, also this one, like you can check, also this one, I'm not sure that is really written anywhere, but one can check that this update is valid, is an histogram, is a Martingale, so is an histogram, and is also the resulting sequence of predictive is a Martingale. And so this one, right, this recursive partition estimator have a lot of nice properties, you know, like in terms of generality of representation. So can be used also, you can easily generalize it to the multivariate setting and essentially like defining a regression estimator from it. So it can be used for non-parametric regression. So you sample this thing from a multivariate histogram, but really is maybe you should just take my word because we're not entering too much into it. I'm not sure how practical it is, this recursive version of the partition estimator. I don't know, I didn't implement it, to be fair. I got excited of first algorithm described in a book by Learning Theory that I moved to chapter 5, which is kernel estimator, like kernel estimator, kernel in the traditional sense, you know, like of Palden, Rosenblatt, like Silverman. So we have a sequence of bandwidth, and essentially here we have two possibilities. Like, so we initialize the algorithm sampling from any base measure, and then we have two possibilities. In this case, it's not that essential for the algorithm to be recursive. It's very fast to calculate anyway. But essentially, like, we have two versions. We have a classical kernel estimator, where every object is essentially scaled by the same bandwidth. Or we have the recursive kernel estimator for rental environment. And so here, essentially, like it's ordered and in the sense that every observation has its own bandwidth. Here, I'm sorry, but I'm using a little bit of visual notation, and I'm defining actually the density, sorry, because I noticed that just now it is confusing. So here one can check if this kernel estimator is a Martingale or not. And well, in case of the classical kernel estimator, there is a result by Biometrica, by West, that is not really examining this question. Essentially, like West is asking why Bayesian are not using a kernel estimator, and try to define a notion of statistical coherence, but the definition of statistical coherence that we use essentially correspond to the multi-check, implies the multi-level assumption, and it tells you that the recursive kernel extension is a multi-level only if and only if the kernel is a Laplace kernel with a specific scale parameter, like you need to fix the scale parameter. We were looking at the recursive kernel estimator, and the recursive kernel estimator you really lose either the distance of the Laplace kernel. Essentially, like you're saying, if I'm doing a kernel estimation with a Gaussian kernel, I don't have a multi-level. I don't have a multi-level. So, are we a bit doomed? Well, no, but we are not gonna see this today. You have to die young. So, what can we do? What can we do when we don't have the multi-level property? And we are not going to look that much at the kernel estimator example. We are going to look at a simpler example, especially because I think that here there is not that simply that much work done. But say, what can we do to check the validity of an approach when the multi-level assumption doesn't hold? In order to do this, I am looking at, for example, at another simple case. So this one I'm defining very informally a bunch of approaches that, I don't know, both Chris, Steven, Gabriel, also Sandra, and Sonia worked on are related to this idea of they can be defined in different ways, like either we have an SGD over the parameter, or we have predictive sufficient statistic, but essentially like we are changing the recursive update rather than working directly with the sequence of predictive on underlying the sequence of parameter. This is another case that commonly violates the multi-level assumption. So let's just look at another simple example where this is violated. So this one, for example, was discussed by Chris and Steven. So we have a sequence of Gaussian evaluated at the MLE. So it's pretty reasonable to think what is my best predictive guess. Well, it's not very reasonable because we can compute the predictive in this type of model, but how to do it is quite reasonable to say I have a Gaussian evaluated at the MLE and I take it as my best possible guess. So in this case, again, I ask, is it a valid update? And I try to look at the multi-level condition. And so again, I plug in my predictive into a conditional expectation. I substitute it. So this is the Gaussian evaluated at the MLE. The simple mean in this case. The only random quantity conditional on the filtration, here there shouldn't be a one, sorry about this. This is yn times 1 that I'm integrating out. It's a Gaussian convolution. So we get the predictive is the following one. So essentially, like, it makes sense. We are integrating out uncertainty over yn plus 1, we get the values that is a bit inflated. So clearly the multi-level property doesn't hold. And so what can we do to obtain asymptotic exchangeability? As far as I can tell, there are three classes of approaches. So, and what can we do? What can we do about it? In order to check asymptotic exchangeability, so this is Sandra mentioned as well. What we need to check is essentially like we need to check that the sequence of random measures that we are defining converges weakly or surely. It's funny that in this literature, I feel that there are many results that we think very deeply about, and in general, the solution are lemmas of Aldous, are just lemma 8.28. So Aldous, evidently didn't give a lot of values as we do, but you know, you can find the lemma 8.2 in Aldous that give you like that as long as a sequence is almost surely weakly convergent, you have asymptotic exchangeability. Here, just just maybe cautionary, I think that there are a lot of people in this audience that are pretty accustomed of proving almost surely convergent, and they can think that it's not really a big deal. But actually, it is quite a big deal in the sense that if something is not announced here, we are losing a lot of regularity property. You know, we are losing this conditional identically distributed. This almost means that even in this simple example that we just look at, we are a bit in the open sea, you know, that we are looking at a new type of dependence that is not fully characterized, that needs to be characterized, but is not fully characterized. So in general, not all the approaches are very trivial. But as far as I can know, I think that there are 3 of them. So the first class of approaches, and I use this Gaussian example because all these approaches can be used to cover the Gaussian example, not the kernel estimator, is invoke some property of the underlying sequence that we are defining. For example, we say that the underlying sequence of parameters that we are defining is an multiple. So in this case, we are working with non-CID observation, but we are relying on the martingale property of the theta n and using that to prove the convergence of the parameter. And since my sequence of predictive is driven by a parameter that converges, essentially I will show you the convergence. And these approaches, I think that we see used at least in 2 instances. One is on the case of the parametric Bayesian bootstrap, and in Sandra's talk we just saw the logistic regression. Note that these proofs are not always innocent to do. And for example, in the case of the parametric Bayesian bootstrap, Edwin, for example, Edwin and review, this is an archive paper, if I'm correct, suggests to work, so this one, in this case, the parameter is updated with SGD. They suggested to work with the natural gradient to make essentially the condition of conversion verifiable. Otherwise, the conditions for convergence are almost unverifiable. That's my understanding, at least, of the paper. So one property is invoking the property of the underlying sequence defined. Similar in spirit, but very different in the proof. I think it's this beautiful paper by Garelli and co-authors, where essentially we are defining a larger class of sequence of predictive driven by the sample mean and sample covariance, meaning that every step the predictive has mean, the sample mean, and has variance, the sample variance. And they really go about proving, let's say, this is the other way, like it's really like proving the convergence of the statistics. And it's I don't know, it's a very nice paper, but this firm is a little bit non-trivial. So all these kind of can be used somehow to cover this Gaussian example that we have just seen. There is another way. So these 2 approaches were working on the sequence of the parameters. Another approach is just saying we are not working with multiple, we are working with a larger class of random measure that is such that under, let's say, checkable assumption converges uniquely almost surely. So for example, with multiple, we are proposing a deviation from the marginal assumption that needs to be controlled by a sequence that needs such that is almost sure summable. This one covers also the Gaussian example, covers the kernel. And you know, but I'm not going to talk too much about it because I'm going to talk about it on Tuesday in the session with Sonia and Edwin. So I'm going to give more detail there if you're interested. We go more into detail. But so 3 approaches, I think, to work with the Gaussian examples. No, like invoke the property of the sequence of parameters that I'm defining, going a bit the hard way, proving the statistics that is driven the statistics, or just working with a larger class of random measure. Okay, so I'm almost done. So I hope that has been clear what we try to achieve. So essentially, like we have this bootstrap type scheme that generalizes substantially, obviously, the idea of the bootstrap, and I think that we can come about inventing these schemes from many sources. At the conferences that was appearing this summer, people are really going far out in this. People are talking about transformers, large language models. So, yeah, bold, but it's nice. And I think that, once you come up with a predictive, we need to check the suitability for these schemes. And today we're talking about, I think the tutorial was around these two themes, like it needs to be valid and practical. I tried to give a little bit an idea of both of them. There are some things that I didn't touch. There is a bit an overlap with the discussion a bit of Sandra as well. I think that an important question, so now I think that the literature is still in the expansion stage in terms of coming up always with new schemes. But I think that there is a valid question which schemes to use. The paper by Garel and Post, I think that there's a lot of quotes that I really like, and they say, well, it depends on the application. But I think that there is something about mathematical properties. Sandra talked about consistency of this procedure. I think that to me, it's maybe along this line. There is, how do we compare the sequence of predictive? So now we are just checking asymptotic exchangeability for reliability. I think that there is another view that it's kind of, because essentially this predictive resampling scheme is going forward. So it cares about the synthetic data, but then we are collecting this data. So at some point we are incorporating that. And so I think that there are almost two-dimensional looking at the scheme. The fact that I need to use them sometimes for estimates, so that's what I say from 1 to n. And then we need to use them to generate fake data, synthetic data from n+1 to infinity. So we have been talking a lot about the n+1 to infinity, but there are really these two-dimensional. And as far as I can tell, the only paper that really does the two-dimension at once is parametric bootstrap one by another view. And I think that there are some interesting things that looking at this dimension. So for example, on Tuesday, I'm going to talk about this kernel example where the two dimensions are almost incompatible. Like the condition for one are usually inconsistent for the other one in the case of kernel. Maybe it's not very clear now, but it will if you recall. Another direction that I think that it's pretty much non-existent revolves around more practical ways of checking the validity of these algorithms. So like all the properties that we are talking about, are mathematical properties that are very difficult to check in difficult algorithms that cannot be studied analytically. So can we substitute this mathematical property with proxies that at least estimate this quantity? Like if we cannot check a multi-year property, can we do a test, for example, on this line? And as far as I can tell, nobody does that. But I think it's interesting because, as I said, people are trying to use transformers or variational family, complex object that cannot be studied, I think, or at least not by me. Thanks a lot.
Thank you, Lorenzo. I think I learned a lot. I guess I have one comment and one question. They're related. So the comment is that by looking at the recursive partition predictive rule, I think that it's valid because it's almost a Bayesian predictive rule because it's looks like the limit of the polynomial tree predictive rule, and then just take the prior concentration parameter to 0 in the limit that you get that. It's just a guess because I haven't looked at the math very carefully. But then the related question is that the first batch of algorithms, if I maybe I should.
Yeah, I'm not sure if it's me or is that no,
differential algorithms, the recursive algorithm seems to be all quadratic. Like every time you update your predictive rule, you have to touch every previous data point. So scales quadratically, which is like very expensive for big data sets. The benefits of using a polyetry type of, in your case, the recursive rule is that the computational cost for updating a new point is proportional only to the depths of the tree, so a constant with a constant multiplier. So I personally feel like that has big potential applications in big data applications, that somehow all of your prediction rules are not utilizing polyetry or some of those computational techniques. So I mean, I don't know if what's the current idea in that.
Thanks. I think this is an excellent point, and actually I have to say that in my initial brain rehearsal of the partition estimator, indeed I was thinking exactly that I should have mentioned that this was pretty natural to see that despite taking it from this partition estimator and a strong reminiscent of Bayesian. So I completely agree on that point, and also on the second part, both algorithms, both the partition estimator and the kernel estimator has this big advantage over the first class of algorithms. They do not require a value to be allocated. When I mentioned like this need to evaluate the algorithm on a grid is a little bit related to that. That the complexity essentially is quadratic, that is exacerbated by the presence of the grid, and neither the partition estimator nor the kernel requires a grid to be evaluated. So yeah, that's why I think that the grid would be indeed offer a lot of potential. And yeah, also the kernel estimator maybe the story being completed is that it can be used for this predictive recently scheme as well, like about related to this last point that I was doing. Yeah.
Great. Are there any other questions from the audience?
Thanks, Lorenzo. That was great. So can you refresh my mind though, in the Holmes and Walker SGD, do they allow batching inside of that, or does it have to touch every data point? If you allow batching, that would somewhat deal a bit with what Lee's point was. So I don't know if they allow batching.
I think that they do it sequentially one by one. I think that it would be also more natural to check the martingale property in this case. So the fact that it's a martingale is essentially like has to do with property of the score, essentially of the thing. So I think that in the batch setup, I wonder whether the same martingale property is still hold. I think that it would depend a little bit how then you construct. I wonder whether, I don't know. I think that would need to think carefully how you think about this batch point from which predictive actually sample from. Yeah, because essentially like that's the driving assumption, that you're sampling things recursively, and that's why the score function has and gives them out the property.
That's a good question. Thank you for the talk. It was very nice. So you hinted at sort of bringing in beyond Bayesian models and looking at sort of like classical or like more modern machine learning algorithms and using that to inspire some of these rules. However, in those predictive rules, it's not necessarily always obvious what is the aleatoric uncertainty bar and what's the epistemic uncertainty bar in their prediction. If there's no clear distinction there, is it still possible to bring them in here, or how would you have confidence in the epistemic uncertainty in the model if that's how you're building it?
Oh, I don't know. I think that there are two things that maybe just thinking out loud of this, like that somehow if you are able to satisfy this property of symptotic exchangeability, essentially like you have that in the limit there is the idea that essentially like in the limit you are acquiring a model and a variable. So that's somehow how you will be able to reconcile algorithmic rule built for whatever reason for prediction, we see more a standard statistical question, a standard statistical framework in which we have a model, a parallel over the unknown quantity that we are about it. So correct me if I'm wrong, we see that we have the author here, but this is very much the interpretation. So one of the contributions, I think that there are, now we often talk about this work on the model that Sandra and Sonia done within predictive inference, but there is another side of the story, which is fitting algorithms within a statistical framework, and within, in particular, a Bayesian story, a Bayesian statistical framework. And somehow this themes of asymptotic exchangeability is what allows to build the bridge. And so somehow then, if you build the bridge using the statistical model, parallel for the statistical model, that's how maybe then we're going to look at the statistical application. I don't know if I'm using the words in that. Yeah.
Well, thank you.
Thanks.
Okay, welcome back to the second half of the workshop. Now we're going to have four kind of shorter research talks, spanning somewhat wider topics compared to before. We're going to start with a talk by Bernardo Flores. So Bernardo Flores, he's a PhD student at UCLA, and he's going to be talking about predictive process. So we'll have about 18 minutes of a talk followed by a quick question, and then we'll move on to the next speakers. So let's welcome Bernardo Flores.
I'm still seeing this in words. How do you make this? I need to point at the computer. Okay. Okay, cool. I will thank you for coming here. It's I will say it's not really okay, so well, I want to talk about this thing I did as a PhD. I don't know. No, it was, I need to remember the name. So, Bayesian inference, so Bayesian parameters is, you know, it's been around for a long, like, several decades so far. I mean, the DP is, how old is it, 25 years old? Like, that's like more than some people here, I think, but not maybe here, but like, so it's what I would say a mature field by now. It's not. There's a lot of literature around, but I think the biggest issue right now we have as a community is computation. BNP models, I mean, everyone that has worked with them know that they don't scale very well. So you know, when you have a lot of data. Well, when you have data, it doesn't matter how much you have. You have two options, right? You either do essential, like without counting the predictive recursion part. You get one CSV, which is very nice, but it's very slow. Or you do variation inference, which is very fast, but to get a good approximation of the posterior can be very tricky. So basically, when you have a lot of data, you have two options, right? You either design a new method, a new inference method to make it scale. But this is a bit hard because it's typically its own data, right? Like it's not, I don't know, depending on what you want to do, it's not trivial, right? It's not something you can do. So it's you either do that or you just throw away the data. All of us have done that in the past. You should basically have a big end, you just take a smaller subsample, and it works. That works because ideally, if you have, say, 1 million data points, you don't need that many. Like a lot of them are going to be redundant. So the question is, how can we do this, but in a more principled way, besides just, you know, just using the sample function now. So, okay, this is like this. So the idea in the complex language and whole concepts, which is there's many definitions, but the definition that I think is more applied for Bayesian statistics is this. So you have data, right? You have data y. And then you just find, you weigh the data, and you find a sparse set of weights, right? So that the inference you get with the reduced data set is similar to the inference you get in the full data set. So, like, for instance, here in this picture that I generated, I don't know if you can see, but the point is, yeah, you have like all these data points, but for all of them, you can choose a reference in that way. So you need something like that, right? And the way this is done in Bayesian statistics is, so it's the way that I do it. So you see how I do it like this, one how I model the data that you want to estimate. And then you just find weights, don't decay, and you assume that they're sparse. So by finding weights that minimize the total likelihood divergence between the weighted likelihood and the non-weighted likelihood, I'm enforcing sparseness. You are essentially reducing the data because you are removing the contributions of some data points. There's a lot of papers, like Carol Daniels has a lot of papers in this, they're very nice, there's some very fast methods to do this. The problem is this doesn't scale very well, not very well, like it doesn't scale at all for high dimensional problem, particularly non-dimensional models, or even those that you have a complex hierarchy. And the reason why it doesn't scale is because, well, you're assuming you can write down the likelihood of this and say this all that stuff at a minimization curve, right? Like typically this is all by using the some variation of it. But well, if you have a non-parametric, you have a BNP model typically they're not nominated, so you can't write down a likelihood like this. But also because if you look at this, so refer to make it less confusing. This W means that it's weighted, and this is the 1 is because it's not weighted, so the weights are only equal to 1. Right? Yeah, okay, so it's only a step of hierarchy models because the problem is being involved in here. So, and each of those, there's a way to actually involve the primary. Well, I guess there are ways, but it's not that trivial to do this. So the question is, how can you make this work in an efficient way for either BNP models or even like extremely, well, not extremely, like complex algorithms? So the idea of how to do this. So as you have this, right, of n, compressed of n, they have a bn because it's large. And we model it with theta. Then we subsample, right? We just take a subsample of size n, small n, or yeah, like this, say you have here a million points, and we take like 50 points as a subsample. So what we found is, okay, what is 7n much likelihoods? We try to match the 0 probabilities. So the general problem comes from like this. So you have the subsample and you have the original data. So you write the probabilities and you will solve this initialization problem. And the ways that minimize this. This, sounds good, but there's several issues to address here. The first is the posterior predictors need to be represented beyond, right? Typically, you cannot, like the most important thing that you cannot get the posterior predictors without getting the posterior, so they need to get away of posterior. And furthermore, you typically are not expecting to get this in a closed form, so you get sample space. Like you need kind of a similar information. So the distance you choose to match instead of the equivalent linear, you choose the associated distance because it's not a very natural way of matching cloud foreign clouds. And the question is how can you find a way of computationally efficiently represent these observabilities without having to reference series. I think I'll just stay here so I can do this. Okay, here. So again, you have a model p theta with a prior pi. So you start with this. Inference model like this, and the idea is to replace this model that can parametric or not by this randomization of it. So as you have a model p theta, what you can do is replace the measure p theta by a random measure set about p theta, right? Because in this way you will get samples, if you sample from this, are similar to the samples you get from its mean, right? Because you have the sample something that's close to its mean. And issues in particular are user process. This is very nice because, well, you know that observability is just that you can just sample from the polyarm. So it's a very fast way of doing this. Okay. So yeah, again, the idea is instead of sampling from replacing the parametric, replacing the inference model, the original inference model, by this non-parametric model, which involves this BP here to be able to sample from the observability. So then with this, you can get a Monte Carlo estimated with this. By sampling from the BP, from the posterior predictive of the digital process, and then finding the weights that minimize the largest time distance between them. So again, the algorithm is something like this, right? So you start with just take a subsample, then you sample the parameter theta from the priors, and then from the hyper priors, and then you just sample. Once you have this theta, you can just start to take samples from the polyarms, right? And just write a little simple optimization routine and obtain these weights. And you repeat this a lot of times for different samples of for different values of theta to explore the whole hyperparameter space. And with this, you construct a Monte Carlo estimate of the weights. Of course, it depends how well this works, depends on how complex good hyperparameter space is. So here you can see some simulations of it. So you can we start with a simple case, which is the density estimation. So if you sample from a mixture and just and try to pick a different mixture, these are not the same. These are not the same models. All you need to do is compare the variance of the estimated mean posterior densities, and you can see that you can get very good performance just by doing a very easy version of this, because you can start with 10,000 points, downscale to 30 points, and you can imagine that what the algorithm is doing is it's finding ways that push some of the data points towards this other mode, right? You start with this mode and then pick, and then just try to separate it a bit more, so you get a better verification of this case. There's no, try logistic regressions, because you see every paper in Bayesian courses uses logistic regressions. I don't know exactly why, but they just like. And so in here the setup is slightly different, because you have well, you have vector, right? So you have the response, which is a 0, 1 variable, and the covariate. But you cannot weigh the response because it doesn't mean anything, right? You cannot weigh the yes and no. So what you do is only weigh the covariates. And again, you get very nice results even in this, like you can say that the corset makes it perform better. Like it just allows to get better quality inference in the sense that you approximate better the inference with the full data. Like again, they will not trying to get the truth because that's not what you want, right? Like you don't want it to, you want to get the same performance you get as with the full data. And then the third is, which is the thing that I found more interesting, is the internal conditions. Because so far there is no way of doing trying to get like a data reduction method for random conditions. So if you have a clustering, if you have a clustering, model-based clustering from a mixture, what you have is you have the issue that you don't observe data. You observe the data, but you don't observe the cluster assignments, right? Which is the thing you want. So you need to include the cluster assignments and just do a data extension, and then just extend the data by, to start with the data YI, and you just add another dimension to it, which is its cluster assignment, and you can run the same algorithm over and over. And again, this works because you can see that what this is doing, what you're doing with the weights, is you're trying to separate the clusters. So you can see that, for instance, in here, if you don't do anything, which is the unit concept, that means just substantive, you take one. You manage to observe only 3 different clusters, whereas with the two data set you get 1, 2, 3, 4, 5. And then with the concept, you can imagine that the algorithm is just trying to push these 3 pointers apart. And you manage to identify more components of this. So the powerful thing about this idea is it's model agnostic, like it doesn't matter which model you want. I mean, it matters in the sense that you will get different performances, you might have to tune it a bit more, but overall it's not, you can apply it for anything including non-Euclidean data. And furthermore, it's independent of the, or whatever downstream task you want. So, because once you have the weights, you can just do whatever you want with the data, right? Because you just have another data set. So if you want to do Hamiltonian Monte Carlo or something, you can do it, right? And it makes it less computationally prohibitive. So, yeah, in summary, what we find a data reduction method based on trying to match the posterior predictives. We approximated the posterior predictives with the posterior predictive of a diligent process centered at the original inference model. And we try to find ways to match the data. This is important because you don't have to find ways. In principle, you can find any transformation of the data. It just becomes more complex computationally. The optimal would be to find what people call the Monge map. It's something from optimal transport. It's not. It's from optimal transport theory. But in principle, you can do anything. It just depends on how good you are at coding. And do that. And yeah, this was it. Thank you very much. That's the QR code for the paper.
Let's just stick with that. I'll give time for one question.
Have you looked at something called support points?
Yes, so support points are similar. Well, support points are a particular case of this. So the difference between support points is So if you see here, this is generally so that all you have a distance and then the relativity distributions. Support points try to find the minimize the energy here, like the B becomes the energy between two distributions. But the problem is they run to the same issue that we did, which is the predictive distributions are not, you have no way, you don't have a way to write this without actually, I mean, if you have a way of writing this, then you don't have to do this. The idea of this is to be able to use this in cases that you don't, are not able to write down the posterior predictors in a way. If you have a method model and you want to use this method, sorry, you want to use support points, you can also do this. All you have to do is basically cycle from the coordinates in both cases, and then finding the way that minimize the energy, which is what support points are doing. So it's not that only have to apply to certain sites, it is more in general.
Thank you so much. Sounds a nice talk. Thank you. Okay, next up we have Carlos from IIMAS UNAM to talk about martingale cluster inference with finite mixture models and clustering. Thank you so much.
Well, thank you very much to Wayne for organizing this beautiful session. I like a lot. Thank you to Lorenzo and Sandra for the earlier talks. Hopefully I will avoid with a lot of imputation and things because they explain it so well. So maybe it's going to be easier for me. So, well, this is joint work with Stephen and Francis. And we're going to talk about martingale posterior inference of mixed models and clustering. This has been published earlier this year in Journal of Computational and Graphical Statistics. So if you want to see any details, you can just look for the paper. Sorry. Yes. Okay, motivation. Well, we are going to focus on inference for the limit mixture model, where K is assumed known, or it could be also assumed unknown. Well, typically we do this in the relationship setting using a complicated MCMC algorithms, could be reversible jump, or maybe better than that processes. But these algorithms, as Bernardo was saying, they are really difficult to implement and to tune, and it's very complicated ideas. So they are high computational cost. They suffer from the Lego switching problem. I know that Lego switching is not good because we are using the NCMC. The Lego switching is because the likelihood of the mixture model is invariant on the permutation of the mixture model levels. So you can actually see it sometimes in the NCMC algorithms. And it's a very curious problem because if you don't see it, it's a problem because you are not exploring the symmetric modes. And if you see it, then it's a problem because you cannot make inference for the groups, hidden groups that are in there. So you have to solve it to at least know what's happening with your algorithm, right? And then if you have this problem, you always in the papers will see a very beautiful density estimate. But you rarely see classification or inference for the individual groups, the hidden groups that we're always talking about, right? Because when you use this model, you are assuming that there are hidden groups, hidden groups within the data. But you rarely see those groups or make any component specific inputs. So our goal here is to use predictive ideas to design a simple sampling-based alternative that completely avoids MCMC ideas and handles all known and unknown K mixture components. And we can recover the density estimates, we want to make inference for the number of groups, and we also want to be able to make a component specific inference. So here is the idea that we're described so nicely before. This is the ideas described in form and with and as well some previous ideas of Kant. In here, you want to find a very nice formula in here to obtain this predictive distribution, right? But if you actually see what is happening underneath, you also they want to always skip this part to find the posterior and to go directly to the predictive using the formula. But if you do the complete thing, here in the underneath is this step, right? That is a marking. And we're using these results of Duke, Martin, the results of Duke, they show that with this process, they can obtain a sample of this posterior. But then what comes and Walker is to look at this carefully and think how to obtain the same results, but under a different initialization. This is what Lorenzo was talking about, right? You start with a point estimate, usually maximum likelihood estimator or moment estimator, an estimator with good frequencies, maybe properties, and then do this one gets predicted. You sample the next observation from the first estimate, and then update this estimator. The conditions that they found for this to recover these results in here are that you have the marginal property and this condition that is the one that is really, really complicated to verify, right? So I believe that those are the challenges that Lorenzo was talking about to actually verify this condition. So how are we going to apply this to our mixed model problem? So our predictive is going to be built like this. This is going to be a mixture of mixtures. We are going to assume that we don't know the number of actual mixtures, but is bounded by a very big number, right? Big capital K. And then we have these model probabilities. These are the model probabilities for each one of the mixtures. And when you select the mixture, well, we just have the usual mixture model. This is going to be our predictive. And first, we are going to sample the number of components using these model probabilities. Once we know the mixture, we are going to sample for the mixture components using the actual weights, right? And then we have to update the weights under the marginal condition. We have to come with a marginal condition to obtain this idea, right? Well, under the marginal condition and this other tricky condition of variance, we can guarantee that we are getting a sample. This is like the general idea. And we can apply the old mixture of Gaussians. We initiate with the EM estimates of with the original data set. And then we update, this is for the known K case. We are going to deal with the unknown case next. We start with the EM estimates for these parameters, and then we proceed with the updates, the 100 predictives, first the Latin variables, and then the predictive ones that we know from which we are sampling, which mixture we are sampling. And then we need to update the parameters using marginal proportions. And these are given here. These are those combination of the weights. These are really easy to obtain. The middle weight is just weight if we sample from the specific component. We also have a combination here. If we don't choose the data component, this is stay the same. And the one that is more difficult is the variance. That is this update for the margin. You can check that these are actually markers in expectation. And well, we have some of these, the one that's kind of difficult. But this satisfy the margin solution. The one that is tricky is this one. Well, I believe that we did something around that for the above all for the variances. We try to do it to show that we are really have that for the variance. It's the effects of the paper, but I believe that we need for more work on that to really show that. And then for the non-case, we need to initiate these model probabilities. We use the archive weights. First, we obtain the archive for all the possible models that we are dealing with. And then we just use a softmax transformation to obtain these weights. And this will be our weights for each of the models that we are trying to make inference. And then we as well have to update these model probabilities again with a context combination. This is a market. And well, we are doing predictive inference. We could use all these parameters that we are sampling to obtain to make inference for each of the groups or classification probabilities. But once that we have the complete population, because we are using the complete population, what we want to do is to use all the imputed data set to make inference for the classification probabilities or for the distribution of the groups. So with all the predicted imputed information, we simply apply the K-means algorithm to the full population, would report only the clustering of the original sample. If you can use any other method, but I believe that K-means is very efficient and works really well. So with all these data that we have imputed, we only report the clusters of the original sample. And well, to preserve the reliability, we run the K-means with the means from the mapping of the initial centers of the K-means. This will preserve the reliability across the different generations. And this data is always goes to the estimator to the mapping. With that, we can then consider classification probabilities for each operation and do classification analysis. Here are the results. These are the density estimates. Well, we, for the galaxy example, these are 82 instances of galaxies that are moving away from our home. And we use the martingale with a BK of 20. We generate 100 complete populations, 50 population of size 10,000. And this is what we get for the density estimates and for the classification probabilities for each observation. So well, here's the procedure for the number of components. We are supporting 5 components in other strategies. We have seen that maybe this support 6, but we are happy with the results. It works really fast. It's really easy to solve. And with other example, the acidic index is a classic example. But when I started with this problem, I was not interested in all of this. I was interested in other problem. I wanted to estimate percentages. So this is really a real data example. All the other things are just examples for me. I wanted to obtain robust estimates for percentages because well, in Mexico in 2021 we have a national referendum to decide whether former presidents should be prosecuted for corruption. And well, this referendum was really problematic because at first the question to be held in this referendum was really aggressive, stating the names of the former president and saying that they are going to be put in jail if they were found guilty of corruption, whatever. The question was sent to the Supreme Court. They changed it to a very nasty thing that no one understood. No one liked the question. It was made, and also the vote occurred with the third wave of the COVID-19 pandemic. The whole thing cost millions of pesos. And people were saying, wait, why would you have to do this referendum? If they are Mexicans, they have to obey the law. If they commit some crime things, why do you need something else? Well, anyway, this referendum was held on the August 1st, and only 7.1% of registered votes participated. That was very low, and because of that very low turnout, no actions could be taken against these guys. Nevertheless, the votes were yes, for school this vote against these guys. No, just 1.5, and null votes 4.66. The problem is that the null votes have a lot of variability. I believe that the guys that were taking care of the polling stations were really mad because people were not showing, and they modified some votings and they put more people vote. So you see outliers there, very amazing outliers, but you cannot discard those votes because it's an official procedure. You have to estimate with these things. So if you select a sample of this small sample of 1,000 polling stations from this population, the estimates are really bad with standard strategies. So I wanted to try this with this idea. I did this first, and then we did the other. And well, this is what we do. We run our mixture model with one number of components. We set K, upper K equal 5. We don't need many mixtures to model these things. And we imputed the votes for yes, no, and new votes, obtaining these are the imputed. And then we estimate just the percentage like this. Right? And with that, we can impute 100 populations, and we will get 100 estimates of the percentages. And we just need the empirical models, 95%, and those were our raw estimates. And well, this is the simulation. We select 200 simple random samples of size 1,200, others of 2,000, and others of 6,000, and compare it with the traditional combined value estimate. This is the scientific mix estimation, and this is the true coverage probability of each method. This is our normal mixture. Well, I as well figure that possible mixture using the same idea. If you see these percentages are much closer to the actual 95% that should be that we aim. So I believe that it works, and it's two data sets, and I think that I was really happy with this. All the rest came later. So that's it. Thank you very much.
I guess this is more related to the end. Were the intervals that wide? I don't remember them being wide.
Well, these are just the true coverage percentages. So you are aiming for this to be 95%. I mean, the true coverage percentage is the percentage of times that each one of the 200 estimates with different samples actually catch the true value.
No, but in the origin, so the motivation was that the original percentages weren't met. But like you want robustness in that thing, but were they very bad, or it wasn't?
Yeah, because at first I was just trying to play with data, and I was first I was this. And I was thinking, in the data set, the original data set, I already deleted 200 observations that were just completely bad. And after deleting those observations, I was getting these true coverage percentages. So I was like, this is awful. I mean, if you get this thing, and you're aiming for 95%. So, see that was the motivation for.
Maybe I can ask a quick question. So you mentioned that the modality, multi-modality problem is less of a problem, right? Predictively sampling. So are your posteriors over like the parameters still multimodal, or is it like uniform?
In which case it is in this?
So for, let's say for the Gaussian data set, like you plot the density estimates, were the posteriors over like the means and the variances, were those also multimodal or relatively?
The thing is that, no, I think, I didn't check it, but they must be unimodal, I believe, because we are trying to aiming for identifiability, because we always start with the EM estimates, and we have the marginal condition. So they never drift away a lot from the EM estimates. I mean, I am almost sure that you can say unimodal. I don't think that they are multimodal, because in that case, you will have later switching problems. Yeah. No, that must be unimodal. But yeah, I don't want to check it. Thank you.
This thing is a mess. That was a nice talk. Thank you.
Let's switch to first.
Be careful with that because it's like super. Okay, great. So next up we have Hristos Sariev. I hope I pronounced that okay. Based at the Institute of Mathematics and Informatics in the Bulgarian Academy of Sciences, and he's going to talk about characterizations of exchangeable Hofstadter decomposable sequences. So take it away.
Okay, in the middle of the presentation, it will become clear why it's connected to Bayesian Predictive Inference. So thanks for hearing me. All right, let's begin. What is Hofstadter decomposition? It's a classical technique which is used to represent symmetric statistics as an orthogonal sum of few statistics of increasing order and degenerate kernels. It was originally used by Hofstadter for the case of an ID sequences to show that few statistics are asymptotically normal. It was later adopted to other problems as well as the setting of something without replacement from finite populations. Now, in these two cases, such a decomposition always exists, but once we introduce some more general dependence between the random variables, this is not always the case. For example, Giovanni Pecati in his PhD thesis talked about exchangeable Hofstadter decomposable sequences, showing that not every exchangeable process is Hofstadter decomposable. And he used the technique to derive some chaotic representations of functions of the Dirichlet process. Now, before we introduce formally the definition of Hofstadter decomposability, let's fix some notation. By boldface x1 through n, we denote the vector x1 through xn. And because we are working with infinite exchangeable sequences, by the definitive representation theorem, there exists a random probability measure p tilde, which is called the directing random measure of the process, and it's such that given p tilde, the sequence is conditionally IID. So Hofstadter decomposition, that is defined. Now, because we will want to define an orthogonal decomposition, it makes sense to work with the Hilbert spaces of all square integral functions denoted by L2, and in particular, we will be working on the subspace of all symmetric square integrable functions denoted by LS2. Now, the composition will be given in terms of these SU spaces. So by SU0, we'll denote the collection of all constant functions, and for each k, by SUK, we'll denote the collection of all U statistics for the k. That is, you pick a kernel in LS2, which depends only on k components, and then you sum by varying of the coefficients. Now, from here, it's obvious that they are embedded into each other. So if they were in addition LS2 closed vector spaces, then these orthogonal differences would exist. So at the end, we get the decomposition of LS2, which is SUN, in terms of these SHK spaces. Now, when our process is exchangeable, these SUK spaces are indeed closed, so each T in LS2 has a unique representation as a constant plus this U statistics for the K, which are orthogonal, that is the inner product here is 0. Now, what happens in the IID case is that the T case are particular linear combinations of conditional expectations of T, which in particular implies that the corresponding kernels are degenerate. That is, the conditional expectation of phi k, x1 through xk, given one less term is 0. And this itself has important implications on the structure of the variance of the T case. And it is this particular property which is used to show the asymptotic normality of U statistics. Now, as Peccati has shown, not every exchangeable process has this property here. That's why we will call an exchangeable process Höflin decomposable if every element in SHK has this representation with respect to a degenerate kernel. Now, because this is not a very, testable condition, he gives an equivalent characterization called weak independence in the case of when the spaces are non-empty. And through that shows that K-core polyomers and also the polar sequence, that is the exchangeable process of DB prior, are Höflin decomposable. Then in a later paper, together with a co-author, they consider the case of binary exchangeable process and show that the only Höflin decomposable sequences are polyomers, IID sequences, and degenerate sequences. That is, x1 is equal to x2, equal to x3, and so on. Sure. Then for general finite spaces, they show that within the class of exchangeable processes, which are directed by normalized completely random measures, the only Höflin decomposable one is the one with the Dirichlet distribution prior, that is the polyomer. So they hypothesized that maybe it was only polyomers and IID sequences which are Höflin decomposable, but in a later paper together with Igor, they construct an example of an exchangeable process which is neither a polyomer nor an IID sequence, but it is Höflin decomposable. And so far, this is the state of the art. So we took upon ourselves the challenge to actually characterize the whole class of Höflin decomposable exchangeable sequences. How do you do that? Well, we wanted some more understandable, at least to us, characterization. And one example is through predictive characterization. And this approach makes sense. Why? Because if you take an F in L2, then you've seen that by exchangeability, the conditional expectation of fxn plus 1, given x1 through xn, is a symmetric function, and it is also square integrable. So it has this representation as a constant plus this U statistics, which are orthogonal. So as a first result, we have shown that for k from 2 to n, the U statistics are essentially 0. So at the end, we get this, the conditional expectation is constant plus the first order terms. That is, so under the condition that the SH spaces are non-empty, then exchangeable process is Höflin decomposable if and only if the conditional expectation has this form here with respect to some phis. So it depends only on the first order terms here. Now, because conditional expectations are typically seen as linear operators, it makes sense to reorganize the phis into an operator lambda n, so that this equation here becomes the conditional expectation is a constant plus the sum of lambda n of f in xi. So you might forget now about Höflin decomposability and just try to answer the question, which exchangeable process have this predictive structure? And this is what we now proceed to do. How do we do that? Of course, first we find some meaningful example, and luckily for us, at the same time we were working on some extensions of polyomers towards infinitely many codes and also general reinforcement mechanisms. And we call these processes measured value polar sequences, and these are stochastic processes with this type of predictive distribution. So it's theta nu plus the sum of r x's normalized, where theta is a positive constant, nu is a probability measure, and r is a finite non-null transition curve. Now, we saw it earlier, but let me say it again. These dynamics here actually can be recognized as generalized on a sampling scheme, where the space of cohorts X is possibly infinite, and we describe all contents through finite measures. For example, theta nu p represents the initial mass of balls in the world whose cores lie in set B. So that the first ball we pick, its core will be generated by the normalized distribution. Then we observe core X and we add new balls, that is mathematically, we add a finite measure Rx. So that's how we get this numerator here. Important distinction, if Rx of X is constant, that is, we always have the same total number of balls, we will say that the model is balanced. First important example is the classical Black-Oman Queen polar sequence, which is a MVPS with reinforcement kernel delta X that usually only one ball to the core. Well known that it is exchangeable and has a Dirichlet process prior. Well known that it is almost surely is direct measure is almost surely discrete and has a stick breaking representation, where I will say that the weights Vj and the atoms, the locations, have a stick breaking distribution with respect to parameters theta. What we did, we started studying whole class of exchangeable measure value polar sequences and found some very illuminating results. Here are the main ones. So if Xn is an exchangeable MVPS and not IID, then it is necessarily balanced, which simplifies greatly the subsequent computations. Moreover, the reinforcement is not arbitrary, but for each model there exists a sigma algebra G such that R normalized is a conditional distribution for nu given this G. Now, from the first result, we can see that every exchangeable measure value polar sequence has a canonical representation where the reinforcement is actually a probability kernel, which allows us to actually reorganize the predictive distributions in this form and recognize that every exchangeable measure value polar sequence is composable. The second result is, on the other hand, useful when deriving the directing random measure, which in this case is again has a stick breaking representation, but the delta uj is replaced by uj. From here, we can derive a hierarchical representation, or equivalently see that the directing random measure of every exchangeable MVPS has a dp mixture prior distribution, where the kernels are actually disjoint. So you might recognize the directing random measure of every exchangeable MVPS as a random history. All right, so going back to the problem of exchangeable Hilbert composable sequences, recall that the conditional expectation of fxn plus 1 centered is just this sum of lambda n's, which we want to characterize. Now I define by curly f the collection of all square integrable centered functions. And as a first result, using exchangeability and some functional analysis, we show that lambda n is lambda 1 over the identity plus n minus 1 lambda 1. So that we need now only characterize this lambda 1. What we found next is that there exists a function between 0 and 1 not included, such that lambda 1 of f is c times f, but not for every f, rather than f in this subspace of curly phi. This is useful because we find an orthogonal decomposition of curly f as this subspace here and some kernels here. So now if we take an element here and apply lambda n on it, we find such a decomposition here. So this is function times f1, f1 comes from here, plus 1 over n, f2 comes from here. This is destroyed. So plugging this back into the conditional expectation, we get this form here, which is not the final form, but rather, in addition, we show that the cxi is equal to cx1 almost surely, and f2xi is equal to f2x1 almost surely for each I from 2 to n, so that we may plug these things outside of the sum and then rearrange again the expression to get this form here, which is very reminiscent of the predictive distribution of a measurable polar sequence, where this is the reinforcement kernel here. So we get this nice characterization theorem for every exchangeable process which has this form of predictive distributions. There exist three quantities: a function c between 0 and 1 not included, a finite sign kernel mu, and a probability kernel r, such that the predictive distributions of a process have this form here. Now, if cx1 is 0, this is destroyed, so we get that the conditional probability is just mu plus mu x1. On the other hand, if cx1 is positive, then we can divide everything by cx1 and rearrange the expression to get something which is actually the predictive distributions of an MVPS. So this is the constant, this is the initial distribution, this is the reinforcement. Thus, conditionally on x1, the sequence x2, x3, and so on will be IID with this distribution mu plus mu x1 in the case where the cx1 is 0, and it will be an exchangeable MVPS with these parameters otherwise. However, this is not a very natural way to, when expressing the distribution of exchangeable process, so we wanted to find another parameterization. If you see, the parameters here are cx1 and mu x1, and we wanted to find something which combines them. And indeed, we show that there exist further two other functions, pi and f, such that c is f of pi, and nu of mu is actually a conditional distribution for nu given sigma p. Moreover, using this sigma p, we can characterize the cases where the process is unconditionally MVPS or unconditionally degenerate. However, notice that there are a lot of cases, there are a lot of intermediate cases. So our predictive distributions now have this form here. So we might again do the same characterization. Now letting p tilde be p of x1, we see that conditionally on p tilde, our sequence is IID with this distribution in the case of f p tilde equal to 0, and an exchangeable MVPS with these parameters otherwise. Now, what is the meaning of all this is that every exchangeable process for which the predictive distributions or this conditional expectation as the formation form with respect to these operators must be either one of the following three things. So either unconditionally degenerate, IID, or an MVPS, or conditionally on p tilde, degenerate or IID when f p tilde is 0, or degenerate IID or unchangeable MVPS when f p tilde is strictly greater than 0. Moreover, we get also an expression of the direct measure effect of any such exchangeable process as this sum here. So it will be either this probability measure in this case, or here the stick breaking representation we saw before, in this case with these parameters. Notice here that this result here is not given conditionally on p tilde, rather p tilde is a part of the direct random measurement. So the randomness here comes from both p tilde and also the weights and the locations here. Was it good?
Any questions? I'll start with the first one. Can you go back to the bias slide? I'm sorry, I've kind of can you give an example of what lambda n means? I think I might have missed it.
Simple cases when it's general. So here, if it is a measured value polar sequence, then it has this form here. In particular, when you're working with the shape of the shape process prime, then this will be delta xi. Of course, this is not here, it's not proven, but I think it should be obvious that among the class of all exchangeable processes driven by normalized empirical random measures, only the one with the shape process prime should be here in composable. And also species sampling models, I think can be put in this form. Except except again the policy.
Something special.
Yeah, it seems so. So I don't know, but I mean from here the cat use the coordinate position. There are some coordinate representation of functionals, and I know that there is some ongoing work by Dario to do the same for repeat maneuver pattern, but he cannot use the Hölder quantity.
Well, let's not speak. Next up, I have a presentation from Professor Jha, who is a PhD student at the University of Chicago Booth School of Business. And you're talking about minimax Bayesian predictive inference with the horseshoe prime. So I think it'll be more the quintessence flavor, which is going to be quite nice to look through these talks. So take it away.
Cheers, Edwin. Yeah, this is a joint work with Veronica Rostrova, my advisor. So, okay, well, so let me just stick with the laptop. So first of all, let's think about a Gaussian sequence model, because that is one of the easiest for examples in predictive inference. We have an unknown sparse mean that is n-dimensional. And out of all these entries, we have Sn many non-zeros. So they will be signals, and the rest will be the noise. And the very interesting setting here is that as n grows, this sparsity level Sn is also growing. However, we're in the nearly black sense, that is, Sn upon n is converging towards 0. And we have the observation that is normal, and this theta is going to be the mean. So the estimation problem, we're basically saying, well, what can be said about theta? For example, the posterior density of theta. But in the predictive inference case, like in our setup, we have a new observation that we call y tilde that comes from the same theta, and it's also normal. And there is an R in the variance that is actually the ratio between the two variances. This is like without loss of generality. If we have sigma 1 in y and sigma 2 in y tilde, and this R plays a role at sigma 2 upon sigma 1 squared, right? So in this case, we assume that this R is unknown. It's known. And what we want to do is to obtain a predicted density that we call P hat. And we hope that this predicted density is close to the true likelihood. So we can already see that there's a connection between the estimation problem and the predictive inference. For the estimation problem, we want a good high theta of given y. And in this case, we want somehow a continuous mixture of it. So put it here. Right. So the primary objective, we want this predictive density to be as close to the true likelihood as possible. That is quantified by the KL loss. And with this KL loss, we can define a predictive KL risk. Actually, it has been already established by Gaurav Mukherjee and Ian Johnstone in their 2015 paper that the minimax risk over all the possible predictive densities is this rate. So our goal is, of course, to find a prior, to calibrate a prior such that the predictive risk attains this minimax rate. So this actually has been done by several papers in the literature. For example, this 2015 and 2022 line of work by Gaurav and Ian, they considered a discrete lattice spike and slab prior. And later on, the work by Veronica considered a Dirac spike and Laplace slab, as well as spike and slab lasso. Well, today we're adding to this toolbox by considering a horseshoe prior. Actually, the horseshoe prior has been studied by Stephanie van der Paas et al., including Art van der Vaart, Botton Sabo, in their line of work in the estimation problem. So actually, that is going to be very helpful for our proof today as well. And so the horseshoe prior. For now, let's assume that the prior of theta is an independent product of all dimensions, with each dimension following a mixture of Gaussian. That is, we have lambda I, that is a shrinkage factor, a local shrinkage factor, and more importantly, we have this tau. Tau is called the global shrinkage factor. For now, let's assume that tau is fixed. I know that some will question this independent products form, but later on we'll see that when I let tau be random, this could be somewhat dependent, right? So intuitively, this tau should capture sparsity, and we shall see that. And we impose a half Cauchy prior on each of lambda I, each of the local factors. And in this case, we can prove that for tau, this horseshoe prior, univariate horseshoe prior, is upper bounded and lower bounded by, well, by this form, which means, well, around 0, we have a natural spike that kind of imitates, for example, a spiking slab prior. And on the tail, this is where things get a bit different. This tail is very heavy. It actually imitates the Cauchy distribution. Well, why do we want that? I'm going to cover that later. So in this case, we know that under the fixed tau scenario, the predicted density has this additive form. Product. It's a product. And then, so the KL loss is additive. And so the Bayesian predictive risk is also additive. So if we want to bound, if we want to give an upper bound of the predictive risk, multivariate predictive risk, we only need 2 parts. The first one is this risk at 0. And the other one is this maximum risk, univariate, of course. And then also with tau and lambda fixed, right, we end up with a normal prior, right, a Gaussian prior. So for each Gaussian prior, we already know that the univariate predictive density looks like this. Actually, this mean is like a shrinked version of the observation yi. And this shrinkage, let's define this thing as 1 minus kappa I, because this shrinkage is always between 0 and 1. We define this kappa I as the shrinkage factor. And then we can write the posterior of this theta as like the posterior of of kappa, right? And since we previously imposed a half Cauchy prior on lambda, this is equivalent to imposing a so-called compound confluent hypergeometric prior on each kappa I, which looks like this. It has a closed form. But that's not important. What is important in this case is if we plot the prior of kappa, we shall see that it has a U shape. And for those who don't know, this is exactly the reason why this prior is called the horseshoe prior. So unlike many other priors, this kappa has a concentration around 0, meaning that no shrinkage at all, and a concentration around 1, meaning shrinkage all the way towards 0. As a counterexample, you can think about, say, a prior that doesn't have a spike, or it doesn't have a mass around kappa equal to 0, and that's the main difference. So why do we want to use the horseshoe? Well, compared to the lattice spiking slab, for example, it is smooth and natural, right? It is a fully continuous mixture of Gaussian. But some may ask, well, the spiking slab in Veronica's paper, that's also smooth and natural. Well, the different thing about horseshoe, I would emphasize 2 points. The first one is automatic posterior phase transition according to the observation, yi. Well, so that is thanks to the powerful detection mechanism of signal versus noise of the horseshoe prior. And the second point I want to emphasize is the so-called, well, I kind of just made up
this terminology. I call it the horseshoe spectroscopy. We will see that under the horseshoe prior, the predicted density and the loss, they can be written or upper bounded as a continuous mixture of the Gaussian case. Right, but before that, let's take a look at the posterior of both lambda and kappa. This is actually where the automatic phase transition lies. So it can be computed that the posterior of kappa follows this rather than axis form. This phi thing here is what we call the confluent hypergeometric function with two variables. And then if we plot it, we shall see that, well, if my y is large with the blue line, we have the posterior of kappa concentrating around 0, meaning that almost no shrinkage or little shrinkage. For the green line, for a median y, we have like on both sides. Right? For the red line, that is a small y, we have, well, then kappa is almost concentrating all the way to 1. And let me tell you, if I have a very, very small y, it is going to collapse all the way to 1. And that is where the magic happens, because there is an automatic phase transition. For lambda, it's the same thing, because lambda and kappa, they're equivalent, right? So the posterior of lambda, it really has two modes, one on 0 and one on non-zero. And we might be interested what is going to be the switching point between like concentrating to no shrinkage at all versus concentration all the way to 0. Well, that switching point occurs around the order of square root log 1 upon tau. So what is it? We shall see that with our optimal calibration of tau, that is exactly order of square root log n upon Sn. That is actually the same order as the detection threshold in the literature where Sn is not growing, right? Then in that case, the detection threshold is square root 2 log n. So it's of the same order. And next, I'm going to talk about horseshoe spectroscopy. It is actually quite easy to prove that the predictive density under the horseshoe prior is a continuous mixture of Gaussian. Why? Because if we fix lambda, then the posterior density, the predictive density under the fixed lambda is going to be a Gaussian. And in this case, we have this posterior of lambda, and this posterior of lambda can be written in a closed form. And that's for the predictive density. And how about the predictive KL loss? Actually, it can be very tightly upper bounded by a continuous mixture of KL losses under fixed lambda I, which again is a continuous mixture, again is a KL loss under a Gaussian predictive density. Right, so that has a closed form expression as well. And again, this time the mixture weight is also the posterior density of lambda. So in the special case, right, in the special case of the horseshoe prior with fixed tau, in this case, from this spectroscopy result of KL loss, we can prove this spectroscopy result for KL risk. This one up here, it may seem a bit nasty. It's actually more intuitive than useful, because we have a bunch of theta there. And eventually we want a superlump over theta, which is going to explode. So this is not really helpful in the proof for theta not equal to 0. However, when theta is 0, we can see that this really reduces to a very convenient form. Phi1 upon phi1. This phi1 again hypergeometric. A confluent hypergeometric function with two variables, and this C is normal to 1 as standard Gaussian. And since we have a different argument here, 5 halves versus 3 halves, this can be comfortably upper bounded. This actually is one of the key steps in our proof of the main theorem. So now we're ready to present the exactly minimax risk result. Actually, this risk again, this is univariate risk, can be written as exactly equals to this thing here. I'm not the first person to do this. A similar result has been done in Ross's paper and Veronica's paper as well. But this n thing here is different. So for the horseshoe prior, our n of z has the form of, again, a phi1 function. So really, our KL risk can be written as the expectation of a phi1 upon phi1 again, just with different b. So the numerator has b, the denominator has b equal to 1. But that is very, very hard to bound. It is almost impossible to directly bound it at all. So, so we need to use these equivalent forms of integrals, and we need to split the integrals. Why? Well, I mentioned one advantage of the horseshoe prior just now, that is the automatic phase transition. And it is exactly the same phase transition that made direct proof difficult. And we kind of have to split cases all the time. And well, but nevertheless, we have an exact form, and we can plot it. And we can see, I actually plotted it under the same R value as the ratio of variance. And I've changed some different values of tau. So when tau is small, we can see that, for example, this red line is a very small tau. We see that the risk at 0, it really just goes down to 0. However, the maximum risk is kind of exploding, it's going up. Right. So we may want to find a balance for tau, such that tau should be positively correlated to the sparsity level. Well, that is doable. Actually, in our main theorem, I shall show that this best value of tau is almost linear to Sn upon n, up to a logarithm factor. So if we let tau take this value, Sn upon n, with log alpha n upon Sn, alpha being anything between 0 and 1/2. So if alpha equal to 0, then what this tau will be, this will be exactly the sparsity rate. And when alpha equal to 1/2, very interestingly, that will be exactly the same rate as in Stephanie's paper, that line of work. Then in this case, with Sn upon n going to 0, that is in the nearly black sense, for any fixed R, we have this, this multivariate predicted risk being upbounded by basically just a minimax rate. And it's not even rate minimax, it is exactly minimax. Because as n goes to infinity, we only have, the only dominating term will be this Sn upon 1 plus R log n upon Sn. Right. So, but, well, you may ask, what if we don't know about Sn? What if Sn is unknown? Well, if we still consider a fixed tau scenario, we can no longer plug in the tau value that is related to Sn. But what we can do, we can let tau take 1 upon n, then we're going to end up with a rate with log n instead of log n upon Sn. So that's where the almost this case is hard, because Sn is growing with n. If Sn is fixed, then well, I have this and it's done. But it's not that case, right? So is it possible to reach a minimax KL risk that is adaptive to unknown Sn? The answer is yes. So we're taking the full base approach. Of course, we can take the empirical base approach. We impose a prior on tau. And in this case, the prior of theta is no longer a product. Right? There are some dependence between all these dimensions. And the rest is basically the same. We end up with one more dimension. We end up with one more expectation of tau upon y. So really, it is important to control the posterior of tau. Right, so I'm going to skip the technical details here. So we can prove that the posterior of tau has a closed form. If we impose the prior of tau, the posterior of tau can just be written as this. Again, a lot of phi 1s. So if we plot it, we see that, well, when the signal is strong enough, then it seems that there is an upper bound and a lower bound on the posterior expectation of tau. However, when the signal is weak, then this posterior will collapse to 0, which is not good. So some condition of signal strength is needed to obtain the minimax rate. So this is where we introduce the Bateman condition. So we asked that the minimum signal strength is C times that threshold. And based on that, we take another route in the proof, proving that for any parameter, the posterior expectation of tau is upper bounded exactly by this rate. And the very interesting result here is that under the Bateman condition, we're able to pick out perfectly the model. We know which ones are signals, which ones are noise, which is very intuitive, right? Because my signal versus noise is separated largely enough. So I'm able to detect them well enough. And in that case, we end up with the second main theorem, that is, in the worst case scenario, what is the worst case scenario of the prior distribution of tau? That is the uniform on 1 upon n to 1. That is, we know that tau is a proxy of sparsity rate, and we give it a uniform. And in that worst case scenario, we're still able to obtain the minimax rate. This time it's minimax rate, not exactly minimax risk, whenever C is large enough. And that's all about my work. And okay, any feedback, questions? Well, thank you very much.
Yeah, so I see you mentioned several times it's like the sort of rate max or min max, and then you said it's kind of different. Can you explain more about that?
Yes. So it has been established early on that the minimax risk is this. So actually, it is a factor 1. But in many of previous works, it's rate minimax, meaning that the factor is not 1. In Veronica's paper, it's 4. So I'm just saying that when tau is fixed, in theorem 1, the risk is exactly minimax, like this. 1.
What do you mean by as a fact?
So the upper bound, it is this minimax rate times 1, and not anything else, not 4. So it's yes.
Okay. That's okay. Good.